curvature of the Earth horizon model of science.
How many of you think that the flat Earth model doesn't make sense because the sun would never rise and set, but instead be visible 24 hours a day?
We know the Earth is round by observing it closely. If you watch a ship as it disappears over the horizon, the bottom will vanish first, and then the top disappears later. It looks like it's sinking, kind of. That's because the Earth is curved.
You know the Earth is round because you can observe it closely, really. Yet when people start really looking into this and they start observing it closely and they don't see any curve, then they'll go and say, oh, well, it's too subtle to see, even when you observe it closely. Yeah, okay. But somehow you can notice it when a ship goes off in the horizon just a few miles away. Something like 30 odd miles. It's really nothing in the grand scheme of things. And you can see it going over a curve there. Yet, when you look at something that's 30 miles away, you don't see it go over a curve. You can still see the whole building. Alright, okay.
One of the most commonly used yet completely false assumptions of proof that we live on a globe is watching ships disappear from the hull up as they go off over the horizon. You may have heard people claiming that roads and rows of pylons appearing to bend down towards the horizon in the distance are also proof of curvature. And of course we all know that sunsets are supposed to be because the Earth is turning and we are watching the sun go down behind a curve. However, it can be easily demonstrated that these assumptions are merely descriptions to fit the narrative that we are on a spinning ball Earth, when in fact all of these observations can be made over a flat surface across a very short distance, which is what we'll see here, looking along this road on top of a dam. This is a straight stretch of road across the top of the dam, and then the road goes around the reservoir. Looking at it from Google Earth, I measured the distance from where I was stood with the camera to where it starts to turn off around the rest of the lake, and we got 650 meters, so just over half a kilometer, not very far at all. So by putting the camera on the ground, we get a similar perspective to that of someone standing on the shore watching a ship go off into the distance across the sea. Keeping in mind that while any surface in nature can be flat, it will always be rugged and never completely smooth like an artificial surface. So first off, we can see this optical phenomenon going on with the railings, which is exactly the same as what is seen in photographs of the causeway and the power lines going across Lake Pontchartrain in the United States, with the claim that this is proof of curvature, when in fact we can see exactly the same thing happening here with these railings. We are below the railings and they appear to bend down towards this band of convergence. The yellow line is the camera's eye level, and the camera's quite level now, so we can see that there is this band of convergence above what appears to be this horizon line of the surface. But this horizontal line is not where the surface begins to curve away from us in any way. It is just as far as we can see from this low perspective before the surface beyond it begins mirroring. This photograph of a fjord taken in cold weather shows the same optical phenomenon happening at the horizon. The purple line shows where the surface actually meets the shore on the other side of the fjord, but then we have this mirroring beneath that and going down to what appears to be the surface of the water. Even with a relatively high perspective above the ground, we soon get this mirroring and convergence. And we'll see as we bring the camera down that the apparent horizon, that hard line of the surface, will come closer to us. The lower we go, the closer the horizon over a flat surface. The surface is still there, sorry about the camera, but it is now mirroring. And as we lift the camera up again, we'll see the mirroring receding and going back into the distance. I'll bring the camera down again and we'll see the horizon come rushing towards us as the surface beyond it mirrors instead of showing us the actual surface. This is why some people will claim that there is a drop in the horizon over distances and that the surface does not appear to rise to eye level, when in fact it does, and the horizon is always at eye level at any height. However, there is this band of convergence and mirroring just below eye level. So when we look across a vast ocean or across a blanket of clouds from high above, we eventually see this convergence, but there is no background color like there is here with the trees. So we just get this transparent band, making the apparent horizon of the surface appear lower than eye level, making it appear as if there is a drop in the horizon when the surface is still there, but it has just become blurred and transparent in our vanishing point. So again, as we bring the camera down, we can see here that the horizon gets closer across this flat surface, and everything beyond it becomes swallowed up in this mirroring and convergence. The railings go back to looking straight again as we gain more height, and the lampposts and the railings are now following the laws of perspective, but as we go down, the railings get swallowed up in this band. As this cyclist rides off into the distance across this flat surface, we'll see the same phenomenon that we observe with ships going off into the distance and assumed to be going down a curve.
Now, first, the bottom will disappear.
When in fact we can see that his feet and wheels are now disappearing, but he is also being mirrored by the surface. So we have the surface mirroring half of that, and the actual rider still on the surface and being observed, even though we cannot see his lower half very clearly. And as he gets further away, there'll be this kind of separation of the two, and we are left with just this top half that seems to be floating above this band of convergence or mirroring from the surface. And this, we will see in a moment, is what we actually see at sunset. We see the sun not going down below this apparent horizon of the surface, but we see first this mirroring, and then as it gets further away, it just disappears, just like the cyclist. I'm going to raise the camera and the cyclist will pop back into view, even though he's on a flat surface. There he is. And you'll watch him go round the corner to the left in a second. So this shows that giving ourselves a little extra height over a flat surface will allow us to see a sunset twice. We don't have to be looking down the curve of a ball.
there's going to be an arrow that pops up here, and I'm going to show you right where this arrow points is where the true horizon line is. This is the sun reflecting off the water that's past that water line. That is your true horizon line. And as the sun sinks, or appears to sink, it's not really sinking. But what I want you to do is pay close attention to the size of the sun right now and watch how it blends into its own reflection. It's basically going to disappear into its own reflection. It's going to get smaller within its own reflection. People say that, you know, oh, if the earth was flat, well, you would see the sun get smaller and smaller and smaller.
And we have shrinkage over here from the noon picture.
Well, when it gets to this point, it does get smaller, but we don't see it with our naked eyes. And this is why I done this zoom in video. Now, what you'll see is right here, this is where the magic's gonna begin. Because if you watch it on each side, it's going to actually get smaller. It is blending into its own reflection. And you don't notice this standing on a shore. Because most of us, again, we are just in awe of such a beautiful sunset. Now, with the camera zoomed in, everything does go black around the sun. And it looks like a black hole. And all the light is in the center of that black hole. So it ain't really a black hole, it's a light hole. And I put out a different video, and I think I called it Window into Heaven, and I actually showed this, but I didn't really even notice it myself back then. But now, what I'm going to do is I'm going to put another arrow here. It was a little windy that day, but I waited till till this video settled down a little bit, and I put another arrow here to show you where that actual horizon line is. It is there. So what you're actually seeing is the sun is shrinking into its own reflection, and nobody realizes this. Nobody sees this. Now, at the point that I put right about here, actually, is I used the zoom tool. I took that portion of the video from that point to the end of this, to this next transition, and I used the zoom tool, and I zoomed in on it, and I wanted to give you a close-up view and a slow motion view of that sun. Now, this is the sun, and it's going to slowly disappear. It's going to do a magic act. It's going to do an illusion. It's going to deceive you because it is going to disappear, but it's going to disappear into the atmosphere. Just like some of my boats that I show that get out to a certain point in the horizon, it disappears back into that mirage, that glass area, that mirroring area, that area that mirrors the sky. So again, I'm presenting this to you as my proof. And again, I don't expect anybody to believe me. They don't have to believe me. But this is what I see. So I've got this thing slowed way down. And this is what I want you to see, how this is working. And how where below this you can see the visible water line, but up above, or above that water line, you can tell that that is a mirroring of the sky. And this is mirrored from the top to the bottom. If you split that in half, it's just mirroring the sun slowly fading away. Now, I am not a professional photographer, but I think that my videos is going to prove to your own eyes what actually happens to the sun. It is a deception. It is an illusion.
First, the bottom will disappear.
So he took the data from the internet and built all the layers of the atmosphere, and suddenly the magic happened and everything started to make perfect sense. And when I say everything, I mean everything.
With 3D software, you can model the atmosphere very accurately using refraction settings. We're not talking about drawing it and making it visible, we're talking about drawing the layers with their real effects on sunlight. Once I discovered it, I told my team, guys, we've got a solution. We can test the atmosphere's effect on the light.
After we had everything fixed, we started to compare it with real life. We actually took some real sunset videos and compared them with both the flat earth model and the globe earth model. And guess what? If you play the 3 videos at the same time, you would not know where the flat earth model is, because it really looks like real live videos.
Many scientists think that the flat earth model can't work because it can't represent sunrise and sunset. What are they going to say after studying this proof? Is it going to make sense to some of them now? They can't ignore the atmosphere, and all we did to make the flat earth model work was add the atmosphere exactly how science represents it. The sun is directly overhead, the refraction is near zero, but you still can't say where the sun actually is. As the sun travels towards the west, the atmosphere creates an image of it for every eye. So anyone who looks at the sun from the same angle as you, but from a different city, will see the apparent sun in a different position. But no one can see the sun in its real position. So if you try to triangulate the sun, you will never get the exact distance. This is like trying to triangulate a rainbow.
Most people do not realize that the air is not transparent. We will use transparent sheets for our example. Also, we will use lighting gels for the water and lower water line. This will simulate the horizon the way it is on Earth. Each sheet should represent several miles. The key people need to understand is that the horizon you see is not the exact horizon. If there was no air, no water, or anything else, the horizon would be lower on a perfectly flat plane. People misuse the word vanishing point and perspective in the flat earth movement, and here I will prove how it works. The first concept is air density. Have you ever driven on a foggy day? You can't see 2 feet in front of you sometimes. Or take this example of the Chicago skyline from what should have been an impossible 40 miles away. Some people ask why the buildings are cut off, but isn't it obvious? Here you can see a cloud of air. What they should have asked themselves is, why can you see the buildings at all if the earth is not flat? Now, what is very important to understand is, air compounds. Every mile, there is more air to look through. This forms a gradient. When we put several sheets of clear plastic in front of the other, they form a wall that you cannot see through. The atmosphere is filled with oxygen, zinc, carbon, hydrogen, and many other chemicals that forms a wall of density. Let's watch the experiment in action. As you can see, the sun gets cut off from the bottom first. But that's not all. There's many things to discover in this experiment. First of all, you can see the light shrink around the sun as it sets. This is exactly what we see in real life. When the sun sets in our experiment, we see a color change, just like real sunsets. One major difference in our experiment is it's on a small scale and it's low budget. The advantage is you can do this yourself at home. We will now compare to the horizon you see daily, but before we do, we want you first to understand perspective. As you can see, things that move to the horizon get smaller and lower. However, the appearance that they are getting lower is just perspective. You prove this by looking at a long hallway. The altitude of every light in the hallway is the same, right? Some people think in the flat Earth that when things hit the horizon they diverge due to optics. And although that's a very interesting idea, we're only working with logical things that we can prove in an experiment. With air density, you can prove sunsets without fancy diverging lines, however true they may be. You can see in our experiment we have lower atmosphere, middle atmosphere, and high atmosphere. Did you know that the air gets thinner as you get higher? This is because of buoyancy. You see things that are less dense separate from things of greater density. This is why clouds float, this is why helium balloons rise. This forms a vertical gradient and gives us a horizontal and vertical air gradient. In fact, the speed at how fast things fall depends entirely on buoyancy. If you drop an item in the water, it falls much slower than in low altitude air. If you fall from a high altitude, you fall faster. When you jump from air into water, you fall fast and then slow. Now we combine all three ideas, and you will get this. Right at the horizon there is a 10 to 20 mile high wall of air. The wall of air depends on weather. Remember, it's a vertical and horizontal gradient. Think of it like a diagonal wall or a ramp to heaven. On high humidity, the wall will be closer. On low humidity, the wall will be further, sometimes hundreds of miles. The air compounds. Well, let's just say the sun sets beyond that wall. It goes behind it. Remember how we said that the further things go, the smaller and lower they appear? Well, right at the horizon, an extremely thin line represented here is the vanishing point. This is about a 10 to 20 mile high wall of air. Also, remember there's clouds as well blocking you in the way. Remember the buoyancy idea? Well, the high altitude air is thinner, so the wall is a little bit further. This is why the sun changes colors before it sets on a clear day. It gets blocked by the buoyant air, and then its bottom is cut off by the heavier air. Now you might be thinking, can a 10 to 20 mile high wall of air seriously block the sun when it's thousands of miles away? Well, of course, and here's a diagram of exactly what you're experiencing. You can see the observer and a line drawn to the horizon. The sun gets cut off when it's thousands of miles away. This isn't to scale, but you get the idea. You can even do the math for this if you like. Draw a triangle, imagine the horizon line vanishing point is about 50 to 100 miles away. Then you will see, even if the sun is high, it will fall into the horizon. In our experiment, what you won't see is how dramatic of an effect the air has on the sun. It tends to dilate the sun's diameter. This is why when you see a sunset, it doesn't shrink as much as it should. It does shrink, but it also dilates. And if you film the sunset from a high and dry altitude, it'll shrink a lot more. Including if you watch sunset time lapses from airplanes, you'll see the sun shrink. I also want to take the opportunity to answer some very uneducated criticisms of the Flat Earth movement. People say, why can't you see New York from England? Well, you can answer them in a word. Air. Also, there's questions like, Why can't you see northern stars from the south? Again, air. Also, let's look at ships on the horizon with this refreshed perspective. What density also affects is the water line. Look at this diagram again. Did you know that the air above the water is filled with more water vapor? Well, of course, right? Buoyancy. So that may not seem important, but it's of huge importance in optics. Imagine if I used these blue gels instead of transparent gels. Would you be able to tell the difference between the water line and thousands of these gels stacked together compounded over many miles? Let's look at some examples. You can see here the boat is almost invisible. Here, the air almost completely blocks it. From far away, this air is dense with water and even reflects the water below. This higher waterline effect can cause boats to not be visible and even cause a slightly higher waterline, occluding the bottom of buildings and beaches. Remember, over the ocean there is waves too. The water in the air sometimes causes a sparkling, wavy fractal pattern when you zoom in on it. This is why using examples such as the Bolivian salt flats, Mount Everest, and other land examples are in some ways better for proving that there is no curve. Since you also need to educate people on compounded water vapor. Also, the water line can cause boats to look like they are floating and other really funny visual effects. Now imagine looking at a sunset over the ocean and what all that air does to the horizon. Well, surely it would cause a vanishing point. Also, clouds compounded add to the long list of obstructions in the horizon. Again, for further research, you should look at converging and diverging lines of perspective on the horizon. Perhaps we can consider the curvature of the lens of our eye and even a camera lens as well to play into this. The sunset we see on the Earth matches one on a flat Earth because of the diameter change of the sun, the shrinking light of the sun, and the sun's path in the sky. However, there are already so many videos debunking a round Earth and proving a flat one, and if you have seen this video up until this point, I would love it if you would do more research on the subject. When searching for the truth, it doesn't matter if the world disagrees with you. If you are right, you are right, and the truth will set you free. Here we will run an experiment and prove that light refracts and even bends in the air. We will show how this affects the famous stick and shadow experiment. We will show that the method by Eratosthenes to prove a round Earth is completely unreliable. We will show how refraction can cause the sun and moon to curve towards you. We will explain why refraction is one of the most important topics in flat Earth and how it works greatly in favor of it. Other topics covered will be the stratosphere, density gradients, Snell's law, Fata Morgana and mirages, Nikola Tesla, the SunCalc website, sunsets, the azimuth equidistant map, the false math of relativity, the diameter of the sun, the moon's face, light speed fallacy, and several other topics. If you want to see specific topics, here is a table of contents. However, we recommend that you watch the entire video, especially the parts on refraction. In our last video, we proved that air density can cause the sun to get cut off from the bottom because air isn't transparent. However, now people have asked about the sun's position in the sky and its elevation angle and if it could truly set based on estimations of its size. I've decided to make one final video on the subject to cover other important topics, a few which have not been discussed yet in the Flat Earth movement. In the experiment, we made sure to make accurate measurements to determine the altitude of a laser pointer using the stick and shadow method. We simulate refraction in the atmosphere using a pail of water. Then we triangulate the difference in altitude. First, you can see the setup of this experiment so you can try it at home. You would need a laser pointer, a pail of water, a thin stick, and a tape measurer. We made measurements and marked them. We ran the experiment several times and with different lights. The stick and shadow experiment method of measuring the sun's distance is one of the oldest round Earth experiments. It was widely ignored for thousands of years by all of the major cultures and religions until the theories became popular again in Europe. The technique involves measuring the height of a shadow compared to the object that casts it. Then you have a right-angled triangle. If you measure the distance of that city to a second city or a city that is 90 degrees below the sun, you can get a very good guess of the height of the sun. Eratosthenes guessed that the Earth might be round because he was unable to get an accurate lock on the sun's altitude from this experiment. It's worth pointing out that the stick and shadow is much worse at predicting the sun's altitude in a round Earth, and it is not even used to do so. The experiment is a complete fallacy, mainly because the atmosphere is layered. These layers create a density gradient. Each layer will refract the light in a different direction because the refractive index of the primary elements it contains will be different. From our example, we prove how when moving from air to water, the shadow will increase, resulting in a lower than expected elevation. The reverse is true when moving from water to air, or more specifically, from a high refractive environment to a low one. Here, you can see us move the water in and out of the path of the laser. There are a few things that happen. First, the shadow length increases a couple of inches. Also, we can tell that the position of the light on the ground has changed. Additionally, the diameter of the light has increased. This works against around Earth, especially when they say they don't see an increase in the sun's diameter at sunset, mainly because the sun would pass through water and other refractive mediums and absolutely increase its appearance if their claim had any truth in it. Furthermore, you can even see the angle change within the water, which is quite beautiful. If we film from under the basin, we can see the sun change positions. To prove that the plastic container does not greatly exaggerate the shadow or light, we remove it from the light. Although it does cause a slight difference, it's not as significant as the water. We take the water out of the container and pour it back in. In this segment, you can watch as the shadow grows in the light. You can also watch the light change positions on the ground. And here, for comparative purposes, we shine a regular light on the stick. Here we show how the shape of the container, such as in the case of a cloud, can do the reverse and shrink the shadow, causing the appearance of a higher sun. We show side by side a ball of crystal and the round water container. At the conclusion of this experiment, we triangulated the values of the measurements to show the difference in altitude. The results are shown here. In a moment, we will teach you how to triangulate these. Many flat earthers say the sun is 3,000 miles up. It is unclear what experiment is used to know the true height of the sun. Our guess is no such experiment will exist anytime soon. In any case, this would mean a 25-degree elevation angle at sunset. Obviously, even with air density blocking the sun, that is hard to justify. It turns out that the sun and moon tend to set on the horizon at roughly 10,000 kilometers away from the observer. If the stick and shadow experiment changed due to atmosphere, the question remains, in which direction does it change? And how does this affect both models? First of all, for every question we answer, there will always be two new questions. We are all on the search for truth. With the exception of the enemies of truth, of course. The question you need to ask yourself is, what model has greater margin of error? A flat Earth or a round one? In the game of pool, the longer the shot, the more difficult it is to make. If you are going to claim the sun is 93 million miles away, even the slightest change in angle of elevation will debunk your model. Let me introduce you to the absolute beauty of refraction. In this video, you can see how light bends in water. In our experiment, the angle was straight, but what's happening here? Why is light bending? Well, the best part is you can repeat this experiment at home. You just need a pail of water, some sugar, and a laser pointer. In our last video, we discussed buoyancy. Well, the sugar dissolves in the water and then goes to the bottom of the pail. To make the experiment even more fun, try adding different dyes or even try adding oil. You can see in each medium the light's angle will do something completely different. This is what is called a density gradient. Our atmosphere is a giant density gradient. It is filled with many different chemicals. The troposphere contains a lot of water. Humidity can be 30 to 70%. The lower atmosphere is mostly nitrogen and oxygen. It also includes argon, helium, hydrogen, methane, and many other chemicals. There is other levels of the atmosphere, unfortunately off limits to citizens. The highest unmanned balloon a citizen has launched into the sky was 53 kilometers. Because of buoyancy, helium and hydrogen rise. Therefore, there is a tremendous amount of those elements in the stratosphere. There is the ozone layer filled with O3, oxygen, and there is the magnetosphere. The magnetosphere can ionize the air, and obviously a magnet can have a profound effect on light. This effect is called the Faraday effect. It's where the polarization of light is rotated while it travels through transparent materials. There are many lab experiments to show electromagnetic effects on light. Also, this is a field that requires a lot more study. Some scientists say that magnets don't affect light, but consider that light is moving at extreme speeds. So a single magnet may not be too noticeable. However, a giant magnetic field, such as the Earth's field, can certainly affect light. As you can see, buoyancy absolutely must separate the elements of greater densities. This means that NASA is clearly not telling us the truth about the elements contained in the stratosphere, and they are probably not telling the truth about the air pressure there either. When hydrogen and helium rise, they obviously do not disappear. No, they settle at the top and they stay there. It is almost unbelievable to say that nitrogen is the most common element in the sky when there is so much helium and hydrogen rising, not to mention other combinations thereof. Take a look at our buoyancy diagram. This is what we call a density gradient. The cutoff lines are actually pretty clear. Let's take a look at a density gradient in a laboratory. Here we can see that the light is bent downwards and then it is bent upwards. In fact, they even split the beam of light and recombine it later. Pretty amazing, right? Still not convinced? Take a look at this clip from the North Pole sun mirage. They see the sun during a time of the year where it should have been impossible. It may be due to the magnetic pole or some other refractive phenomenon. There have been many experiments to show how light can bend up or down in our atmosphere. Over the water, it would be more probable that light bends downwards very slightly near the ocean line as light descends. This is because, as you get closer to the water, the amount of water particles increase. This increase in density causes light to go from a refractive medium to an even more refractive medium. This is called Snell's law. This could add to the list of possible causes for cities to get cut off at the bottom over the water line. What's cool about Snell's law is when you send light back angled up from the water, the light can actually bend upwards. This has been seen in different flat earth laser tests. The experimenter has to be extremely careful to keep the laser as straight as possible, and over several miles that becomes almost impossible. Imagine shooting a pool ball into a hole 10 miles away. Snell's law is basically an equation that is used for calculating the change in angle of light as it passes from one medium to another, so we can mathematically compute and guess how much light might bend in each medium. Let's take a look at a refraction simulator online. First, you can calculate light going from air into water, like in the case of a city. Remember, the city is on land, so the water density is lower there. As you can see, the lower the altitude of light projection, the more the light falls when it hits the water. As you can see, the sharper the angle of the light, the more the light falls when it hits the water. This works in favor of a flat Earth in any case, because a city's skyline would have more trouble curving over the horizon when moving from air to water because it refracts light downward slightly. However, if you are in the ocean and you shine light upwards, the reverse happens. Let's take a look at what happens when we go from water to air. Amazing, right? The broader the angle of the light source, the less it refracts. Although in our atmosphere these changes are subtle, they are significant over many miles. Let's take a look at this site here. They sort some elements by their refractive index. Notice that there are still tons of materials not on this list, and they do state that the numbers need to be verified, but this is a great reference. So we can see that hydrogen is 4 times more refractive than helium, and lucky for us, hydrogen is more buoyant. So for the 300 or more miles of atmosphere, depending on how high you guess the sun to be, light will travel significant distances bent upwards towards the observer. Extreme heat or cold from the sun can certainly forge elements, such as helium hydride or even stranger elements. It's fair to say, unless parts of space reach negative 300 degrees, we will probably not see liquid hydrogen. However, on the internet, people seem to say in some cases atmosphere is extremely cold. It creates an inversion layer, supposedly. Maybe it just depends on where the sun is. It has been estimated that there is helium hydride in the stratosphere, however. Now, if we consider that hydrogen is above helium, this element will form a nice little lens compounding the amount of refraction that the light experiences. Even a thin layer would be significant. Imagine the light passing through hundreds of tiny little lenses. In order for helium hydride to exist, it must be in an excited state, and I think the tremendous heat of the stratosphere would be a good catalyst for this. I would like to see some experiments done with refractivity of exotic materials like these. I expect it to be significant. You see, an element on its own is not even close to the refractive index of a combined element, and the direction of refractivity may indeed change depending on the combination. For example, water is significantly more refractive than hydrogen or oxygen on their own. Why the dramatic change? Because the elements form a little lens. Let's take a look at the periodic table sorted by density. Using this, we can know how some of the elements will be ordered in the atmosphere and what direction light will bend for each layer. But don't let that dominate your calculations, because what matters is the amount of miles light will travel at the angle before crossing into the next medium. Also, it matters greatly the different materials in the atmosphere. Do not limit your bias to elements only. Refraction increases dramatically when you combine elements. For example, how does ozone affect and refract light, and how thick is the layer? Don't count on government space agencies for honest statistics here. For example, when light goes from helium to lithium, lithium is only 0.23 refractivity, and helium is more than 4 times more refractive. So again, light refracts upwards, and quite significantly. Lithium passes to argon, and light will refract downwards, and it will go down again from argon to nitrogen, and then again slightly from nitrogen to oxygen. However, a big change will happen when light passes through the water in the upper atmosphere to air, which will refract light upwards again. It's hard to say how much argon or lithium is in the atmosphere, however. Ionized particles need to be considered too, and particles such as dihydrogen, dioxygen, and so forth. It's no surprise that people see sundogs and other anomalies in the sky. If you consider that dihydrogen might exist in the hydrogen layer of the atmosphere, then when moving into helium, the refraction angle will be very significant. Light will bend for potentially hundreds of miles up towards the observer. One quick note before we proceed. Explaining our world is not easy. We realize that there will be some debate over how much light is refracted, at what point light refracts up or down, whether or not there is a dome, and so forth. We are not trying to add to the list of theories. We are simply pointing out a scientific fact that absolutely 100% must be discussed. I'm going to assume that because of how many factors there are involved, that being able to calculate this mathematically is actually impossible. However, lucky for us, we have evidence that works in favor of flat Earth. It's called advanced sunrise and delayed sunset. This is where the sun sets later than it should. Sometimes the sun rises earlier than it should. This is evidence that sun's light bends upwards towards you. In fact, even according to Wikipedia, which is usually very anti-conspiracy, the sun has been seen to set and then rise again, only to set and rise within the same hour. This can be found under the entry for atmospheric refraction. Although I don't really like using Wikipedia, since news articles have been published showing the majority of Wikipedia edits in some categories come from CIA data centers. But let's use it anyways to get some ideas. First of all, their image for the sun is totally bizarre. Why do they have the sun's rays pointing upwards and then bending downwards? Don't the majority of the sun's rays come in straight? In fact, if the atmosphere bends light towards us, why does it ever get dark? Isn't the sun billions of miles in diameter? Anyways, the actual diagram should look something more like this. Here the light comes in straight and bends up, just like we calculated. First off, it says astronomers will never shoot a star 20 degrees below the horizon because of refraction. Then it says that refraction is caused by the temperature gradient, the temperature, pressure, and humidity. This is extremely interesting. Did they forget the refractive index? We just got finished looking at refractive indices, and they ignore it. But they add some useful information, temperature. This is a huge factor in refraction. You see that the atmosphere gets extremely cold in some places and extremely hot in others. You will see how much this matters in a moment. Here they say something else. They say, when the bottom of the sun touches the horizon, its true altitude is negative. Did you see that? That means it shouldn't even be there. And since they are assuming a curved Earth, imagine if they assumed a flat Earth. That would really change all of their calculations. It then talks about an example once of how the sun set only to rise again an hour later. That's right, an hour later. And then it set an hour after that. And then it rose and then set again within the next 20 minutes. This is a classic example of advanced sunrise and sunset. Then they give some formulas, although these formulas might be kind of useless because they would have to know the exact elements contained in the atmosphere and the changes in temperature, especially in the thermosphere. And then a calculation so complex would never be reduced to such a trivial equation. However, this formula is interesting. Here it says the amount of refraction increases 1% for every 3 degrees decrease in temperature and increases 1% for every 3 degrees increase in temperature. How these were arrived at is not really clear. It looks like they base this off of the previous equations and more assumptions. The numbers seem way too linear, but if this is true, then the extreme cold or heat would dramatically change refraction. Is there an experiment we can do at home to prove this equation? Probably not. And I'm sure it wouldn't really give us any help on the extreme heat of the sun and how it affects things. After all, on a hot day over the road, light starts bending all over the place. We can probably just relate this to pressure and density. Cold air is more compact with more molecules, and hot air disperses with less density. So that affects the density gradient. This is why hot air balloons rise. They say you can see certain dispersed wavelengths with a refraction corrector, which is a rotating prism. But I doubt this would work over long distances because that light could easily be blocked and reflected. Also, the refraction of light makes the calculation of stellar parallax completely impossible, especially on the ground. In fact, Refraction pretty much debunks the idea that stars are traveling up to 1 billion light years to reach us. The probability that light would be refracted, curved, and generally moved all over the place, it may as well be 100%, since they're saying that there are stars that are quintillions and septillions of miles away. Even a change in a trillionth of 1 degree would cause the light to miss the Earth completely. At the very least, you would see stars disappear for a little while to reappear again. Have you ever watched a light moving in water? Notice how it bounces all over the place? It's convenient for NASA that they'll tell you that space is just infinite miles of vacuum, even though they've really never been out there. This is probably another reason they tell you the galaxy and solar system are flat, to avoid the amount of protests they would get otherwise. Also, if astronomers avoid filming stars 20 degrees above the horizon because of refraction, that alone is enough to prove to you that their calculations of parallax are not scientific or reliable. If you triangulate a 10,000 kilometer sunset at 300 miles high to the ends of the stratosphere, we get a 2 to 3 degree angle of sunset. This certainly makes the sun easier to block with air. In fact, anything within 10 degrees is worth discussing. Another reason why this subject is so important is because it can potentially explain why the moon only shows one face. Flat earthers tend to ignore this problem. The moon, no matter where you stand, shows the same side. What type of magic holography is this? Well, if you consider that the atmosphere is potentially bending light towards the observer, then it makes sense that a flat light would change its angle towards us in the atmosphere. Let's take a look at some different types of holography while we are on the subject. Here you can see a coin appear on top of a cylindrical base. No matter what perspective you view the mirror, it looks like the coin is sitting on top of the base. Try to grab it, it's not there. The trick is in the mirrors on the inside, a brilliant little design, like a cylindrical pepper's ghost. Of course, there are almost endless ways to design a system like this. Now let's take a look at lumographic lenses. These things are completely awesome. Depending on the angle that you view the lens, you can see a different image. This type of lens is an art form. And here is Castayer augmented reality glasses. They use 2 projectors and reflect them off of a retroreflective surface back to your eyes. Everyone sees a unique image. Anyone can make a pyramid hologram at home. Here I filmed a holographic moon myself using a simple pyramid made from my transparent sheets. For those people who theorize that there is a dome or firmament above us, whether it is made of ice or any other material, that could definitely reflect light back to the observer at various angles. In addition to reflected light, there is projected light. Light from a projector expands as it moves away from you. However, this also depends on the shape of the lens. A flat light source like a television screen would cause almost no increase in size as you move away from it. Perhaps this is why the moon and sun have a slightly round appearance. It would also be another possibility to explain why the sun does not shrink as much as people anticipate. Also, the further you are from the sun or moon, the sharper the angle is to them and the greater the refraction. Also, the more miles the light must travel through the thermosphere to reach you, and the more profound a small change in angle will be. Have you ever seen a moon set? Have you noticed that it almost always seems to move faster in the sky the last few moments as it descends? The sun seems to do the same thing. Right before sunset, it quickly drops a few degrees. Why? Finally, on this subject, we can see hundreds of examples of sundogs, double suns, double moons, and other things like this in the sky. It's hard to make sense of these sightings and decide which ones are valid. However, multiple suns is a pretty common occurrence. Also interesting is the alleged sighting of Rahu, which is a semi-translucent disk said to be the cause of eclipses. Something similar to this could cause the moon's phases. Or, considering that the sun and moon are constantly refracted, this introduces a wide new range of possibilities for the moon's phases. So let's check out a website called suncalc.org. Many flat earthers come to this site to attempt to measure the sun's height in the sky by triangulating elevation angles. First of all, how does SunCalc know the elevation angles? It doesn't. They guess them based on what they believe the curvature of the Earth to be. Although the angles have just been completely disproven, let's make some observations. If we use this site, we can find out that the sunset almost always happens at 10,000 kilometers away from the sun, or 6,200 miles. This means roughly the elevation angles the site gives you will go down 9 degrees for every 1,000 kilometers from 90 degrees dead center. You can test this yourself. There will be some variations. Let me show you how to calculate the sun's height in the sky. It's easy when you know how. I chose a city that was on the equator, with a 90-degree elevation angle to the sun and at sea level to make this very easy. Then I chose multiple cities at random. I will link my choices and results in the description. Now we measure the distance of our cities by using the longitude and latitude. I'm going to use Google Maps. However, before I proceed, there's one thing you must know and never forget. Google thinks the Earth is round, so that will cause distances of cities, especially at long distances, to be wrong. Google also uses the Mercator map, one of the most blatantly inaccurate maps ever drawn. Greenland on that map appears 13 times larger than its square mileage. The equator is moved downwards, and the northern hemisphere is drawn almost twice as large as its actual size. Countries that are anywhere from 10 to 50% of the size of other countries are drawn much larger. The excuse given was, it's hard to turn a ball into a flat map. But that doesn't explain why the northern hemisphere was so exaggerated, nor does it explain why Mercator chose to shrink some countries while he greatly exaggerated the size of his European employers. At a very minimum, the map is racialist. There is other map options too. Google could be using the Peters projection, which is far more accurate because at least Peters tried to draw the countries more true to their size. Why in 2016 does Google still use this ridiculous map? So is there a map that accurately shows the size of countries? Of course there is. This map is called the azimuth equidistant map. This map projects the countries on a circle, each one being the correct distance in relation to the center point, the North Pole. The Egyptians used this map for stellar maps. It matched the stars. They will try and tell you that the southern hemisphere is exaggerated, but is this true? No. If you look at the size of Africa and South America, they seem to be almost precisely drawn the same size as their square footage. Also, if it is inaccurate, then why do many modern star chart planispheres use the polar azimuthal equidistant projection? In the case of radio, this projection allows for directional antenna aiming, especially in the case of HF communications. So the answer here is, it is used because it is the most accurate map we have. This is why it is the UN flag logo, and this is why flat earthers use it. Round earthers will argue that Australia is not in the right position, but it is. This is why you can calculate sunsets 10,000 kilometers away from Australia, and this is why the sun almost never appears south of Australia, and why the azimuthal equidistant map works for all telecommunications and projections. Another point here is you get 24-hour sunlight near the North Pole during the Arctic summer, but you never get this in the South Pole. You can prove this on SunCalc, which will never show the sun to be south of the tips of South America and Australia. Also, there is one piece of footage that was claimed to be of an Antarctic summer, but that was debunked as fake. As for flights in the southern hemisphere, such as Qantas, Chile to Sydney, you can see a video of that flight, and the video shows it traveling over ice. It also shows the passenger speaking in Spanish, very frustrated that the GPS disappeared and stopped moving in the Pacific Ocean. Well, the GPS probably disappeared because they didn't want to show them where they were actually going. If you head west on a globe straight from Chile to Sydney, you would never detour south. So the only way you would see ice is if you traveled over the North Pole or nearby it, which is exactly what they did. There is almost no direct flights in the southern hemisphere. The ones that claim it are constantly delayed, or you have to phone in where they end up giving you a different flight with a stop, or they're extremely expensive and the sites usually list clearly incorrect flight times and hours and other confusing data on the sites. The reality is that there's almost no direct flights, and the ones that do exist could probably fly a little bit faster without the passengers knowing. There's already many videos on this subject. All flights mapped on the azimuthal equidistant map are almost always straight lines, because why would the pilot waste gas? On a round Earth Mercator map, impossible nonsensical detours are made. Okay, so when we have our distance, we can then find the height of the sun. So far, a few assumptions have been made. First, that the distance we have is 100% accurate, and second, that the elevation angle given by SunCalc matches the actual elevation angle at the day and time you are trying to measure it for both cities. The first city must be 90 degrees below, and the second city must be the exact distance, and you need to know its elevation angle. For now, let's just use SunCalc's numbers so you can see how it's done. After all, this is only to show you how to triangulate. We now have all the variables required to calculate height. We then go to a 90-degree triangle calculator. We enter the distance to the city below the sun, and we enter the angle of elevation, also called the altitude, and voila! We get the height of our sun. Now, this same method was used by the infamous Eratosthenes thousands of years ago using stick and shadow. By the way, isn't it ironic that round earth believers will mock flat earthers saying we believe in old theories, yet they constantly use a guy who's been dead for 2,000 years as their go-to argument for sun angles, even when for those 2,000 years the leading theory was flat earth? Round earth was only popular in European-ruled countries, and even then it was unproven and constantly debated. Only when there was the advent of radio and television and then NASA went to the moon did the world change its mind. Anyways, Eratosthenes used a stick and shadow method for measuring the height of the sun. However, he was unable to determine the height, so he assumed we were on a curve. You see, if the Earth is curved, you only need to know the angle of elevation, and not the sun's distance. Very convenient. We don't have to care anymore. You see, in a curved model, the sun can be anywhere along the same tangent as long as the diameter of the sun matches our perspective, because in this model, the sun's not moving relative to the Earth. Even though they say it zips along the universe at a zillion miles per hour, however, the problem it avoids solving, it creates hundreds more. For example, if you try to calculate the sun's distance using known cities with the assumption of a curve, you get some pretty ridiculous results ranging from 1 million to 100 million miles. Sometimes the stick will be pointing away from the sun and you won't be able to calculate it properly. Imagine trying to shoot a pole ball into a hole that's 100 million miles away. Could you do it? You can see how many times the sun's estimated distance has changed for the round Earth model over the years, with margins of error of 100-fold. This obviously is not the scientific method. You have literally zero margin of error, and it absolutely does not match what we measure with stick and shadow when we are strictly trying to know the sun's height. So why would people who believe in a round Earth force flat earthers to follow strict measurements that they themselves don't follow? How can a citizen determine the sun's distance on a round Earth? They can't. Only space agencies claim to do this, and here's why. You see, calculations of the sun distance have been made by looking at the alleged parallax of Venus over the sun. They don't share the intimate details of this test, and I doubt it could produce the same results twice. This number cannot be calculated without assuming the distance, trajectory, and speed of Venus, assumption built on top of another assumption. They say they determine Venus's distance by transferring radar signals to other planets, something based falsely on the speed of light, which we will discuss later. And of course, results that can only be confirmed or denied by government space agencies. Because, you know, you and I aren't going to be able to fly to Venus anytime soon. The flat Earth model does not believe that planets are terra firma. They are just lights, which makes sense because they appear to emit light. The flat Earth doesn't make many assumptions. Instead, they constantly research and they perform scientific experiments that anyone can perform. Although in this video, we have speculated on different theories for the moon and chemical makeup of the atmosphere. However, this is done to hopefully inspire more research into the subject. The stars and heavens remain mysterious until we know otherwise. This follows the scientific method. Until the problem is solved, we remain agnostic. However, there is a lot of videos on the subject of CGI and how preposterous NASA's images of the planets are. It's like they don't even try. Okay, so the results of my experiment were as follows. As you can see, the sun appears lower the further away it is from the center point. Why is that? Because they're assuming a curve, so that would cause the predicted elevation angle to not have our distance in a straight line, causing a steeper angle up until sunset. Using SunCalc, the closer you are to the sun, the higher the result. Keep this in mind because the higher the sun, the higher the elevation angle needs to be when the sun sets 10,000 kilometers away. This means the more air that it needs to block the sun, or the lower it must appear due to converging lines of perspective and, of course, refraction. Also, I've noticed that a lot of people do the stick and shadow experiment in relatively nearby cities, and I've noticed that there isn't really that many stick and shadow experiments done near sunset. Anyways, we are not going to use SunCalc. We are going to use real measurements from real people. And guess what? It's extremely hard to find anyone on YouTube who filmed themselves using the stick and shadow method and gave their time and GPS location. But I did find one video from Poland made in 2013. Let's take a look at their results. Here is the link of SunCalc for you to calculate the angles from the results of the Poland experiment. Now at this location, SunCalc says the elevation angle is 45.73 degrees. SunCalc is usually set for a universal time, and they might subtract or add hours depending on your IP address. In our case it was UTC minus 7, which is 3 a.m. UTC, which is 10 minus 7, which is exactly 12 p.m. in the time they listed in the video. The Polish kids measured 43 degrees. That's off by almost 3 degrees. But of course, these angles will never be accurate because of refraction. So if the Earth is round, then why do the results of these kids not match Suncock's predictions? If we were to triangulate that shadow to calculate the sun based on a curve, we would never make it to our 93 million mile sun. But in a flat Earth, it's okay because the sun is close and we care about knowing its nature and distance. So now I'm going to choose a city on the equator. I chose this location. Okay, so that's apparently 4,880 kilometers away from our Polish kids. This makes the sun roughly 2,830 miles high. Great. So now we know why flat earthers thought the sun was anywhere from 1 to 4,000 miles high. So let's now find out the angle at which the sun should set. Remember, 4,880 kilometers is extremely far. That affects our results too. So let's go back to our triangle calculator and plug in these numbers. We assume the sun will set at about 6,200 miles away, or 10,000 kilometers. Now we get 24.5 degrees for the sunset. For the time being, let's ignore refraction, because now I want to talk a little bit more about air density. If we use our triangle calculator, we can start to find out how far and high our wall of air needs to be to block the sun at this extremely inaccurate angle. This is being done just to prove a point. At 50 miles away, with 20 miles of atmosphere, there is 54 miles on the hypotenuse of lower atmosphere blocking the sun. That's 54 miles of dense atmosphere, clouds, water, and other things constantly refracting the light. That's at an elevation of 21.8 degrees. However, it's below our target, so why stop there? The atmosphere extends 300 miles upwards at least, according to the internet. First, let's show some other possibilities. If we assume that after 80 miles away and 50 miles high of atmosphere, we get 32 degrees, which is far beyond our target. We can obviously play with these numbers to look at different angles and distances. We can even calculate a 24.5 degree angle to 6,200 miles and determine how much air is included on the hypotenuse with each mile of elevation. Now, why was a 50-mile high wall given as an example? Well, because the atmosphere doesn't stop at 20 miles, that's why. And beyond 50 miles is the thermosphere, and they consider that outer space. In fact, even at 50 miles, you can still have clouds called noctilucent clouds. If you check online, you can even see different air density estimates for different elevations. But who actually goes higher than 20 miles to measure those numbers anyway? Oh yeah, that's right, government space agencies. So we're back to trusting them again. But wait, if air pressure is so low, then how the hell do we get clouds above 50 miles? Well, they say those are rare. But here's the thing. Those clouds can't form without some sort of density and molecules in order to form them. So just because there isn't clouds doesn't mean there isn't molecules. That's why the sky lights up so bright for the sun and changes colors when the Earth's magnetic field causes the aurora and ionizes different chemicals in the air, which causes all kinds of beautiful colors. And even where it appears dark, there is still very much something there. The two most buoyant chemicals on the periodic table also happen to be ordered first, our old friends, helium and hydrogen. The world record for altitude in a balloon was 32 miles. That should tell you something, that the air in the balloon was not enough to blow up the container. Then it popped, of course. So, okay, apparently there is enough hydrogen up there to form clouds. Remember, things that are less buoyant are not necessarily less refractive. Everything depends on the element. Considering that, on a clear day we can see 50 miles ahead, but then we can't see through the clouds right above us. That means that the high altitude air can also be effective in blocking the sun. It depends entirely on the elements there, such as the makeup of a cloud. Considering they say the atmosphere stretches 300 miles up, and at only 30 degrees, you have to cross 600 miles of molecules on the hypotenuse. Look at this company, Air Swimmers, for example. They make these balloons that look like flying fish, and they just hover in the sky. How do they do it? Well, you find the perfect buoyant balance to the fish by adding and removing putty, and then you can get it to suspend in midair like a cloud, and then you propel it with its fin. Any balloon can be made to hover mid-air if the correct balance is found. This is most likely one method on how airships can find balance. For example, if you had an air intake, you could probably find the perfect balance to keep the balloon stable in the sky. I should also mention that heat also plays a role and causes air to expand, changing the volume. and thus heat is another method to increase elevation. It may also explain why parts of the thermosphere is less dense to begin with, because it's hot near the sun, and when things cool, they contract, so consider all of this. There are even more elements at play when we are seeing the sun set. First, there is perspective. Can we see the sun? And second, there is whether or not the light is lighting us. The two are not related. For example, even when the sun is blocked by the clouds, it still lights us. The reverse is also possible, and I will give you an example. Let's take the example of the moon. The light is extremely powerful, but it doesn't light up the whole atmosphere. The moon's light doesn't appear to have the same qualities that the sun's does. However, it's still visible. Another example, a small light in your house only illuminates locally in a corner, but it won't light the whole room. In fact, the rest of the room might appear dark. Lastly, if we go into the depths of the ocean, the light is always blocked by something. It never travels far. At the ocean depths, light won't even go more than a few feet. This is important because flat earthers have said diverging perspective lines can cause the sun not to be seen. However, they probably didn't consider that the light could illuminate things near you. However, when you add refraction, then the light might not reach you. This is why air density is important. Okay, but let's not rely on converging lines. Let's try to explain perspective with converging lines. Now, if the sun is at a higher angle, why would it appear on the horizon? Well, first of all, the horizon we see is not the true horizon. It must be a little higher, as proved in the air density video. Second, as things move to the horizon, they appear lower, and the altitude of things make them appear angled. This is why it's so extremely hard to determine how far stars are. To us, they are lights in the sky with no apparent parallax. Without parallax, the only way to know a star's position is triangulation. But for that, we need to know the angles to the stars. But you can't know the angle of something based on its visual appearance alone. You can see where it starts getting difficult. Our eyes triangulate things, but the further something is, the harder it is to determine its distance because of perspective. This is also true for multiple cameras and 3D triangulation of points. It's a common problem in computer science. That's why 3D reconstruction is so much easier with parallax and distortion of known patterns, like in the infrared projector on a Kinect camera, or by using multiple photos. If you enjoy the subject of perspective and higher level math, then I'm going to recommend you watch videos about projective geometry by Norman Wildberger, who gives amazing PhD level lectures on the subject. This subject used to be taught in all schools before the 20th century, but they stopped teaching it for some reason, something that Norman laments. He seems to think our math has actually gotten less rigorous. Perhaps that's why there was so many good artists in the Renaissance period. So let's take a look at this video by Phuket World. The video is actually pretty brilliant. He shows not only the size of things getting smaller as they approach the horizon, but how they also seem to be affected by the angle of approach. In this example, the vehicles converge to the center point of his measurement. Despite going straight, they all seem to converge to the center at 23.5 degrees. This is a funny coincidence that his observation matched the round Earth proposed axial tilt. What he also shows is that over and over again, things dip below the camera's perspective despite being on a flat road, mostly because perspective and extremely small bumps in the road. Also, our eye's lens is curved, and so is the lens of a camera, and this is something that I don't really see discussed often. Now, we already know that wide-angle lenses causes things that are far away to curve. This is why fisheye lenses are totally ridiculous choices for filming the horizon. But at what point does the lens in our eye affect the angle of elevation, and at what point does it cause things on the horizon to converge? After all, the further away something is, the more likely it is to be affected by the curvature of our lens. You can try a pinhole camera, but the pinhole camera model does not include, for example, geometric distortions or blurring of unfocused objects caused by finite-sized apertures. It also does not take into account that most practical cameras have only discrete image coordinates. Its validity depends on the quality of the camera, and in general decreases from the center of the image to the edge of the lens, and distortion will increase. So how can we know with 100% certainty that our visual angle to the sun is not affected by any of these things? And can we know that light from the sun can reach beyond 6,000 miles away? Especially when light doesn't travel more than a few feet in the depths of the oceans. After all, when an eclipse happens, it gets dark, but we can still see the sun. So what gets illuminated and what can be seen are separate issues completely. If the vanishing point is slightly angled and the objects that approach the horizon appear lower, it's also unclear that you would be able to visually prove that the sun cannot be flush with the horizon or diverge below it due to optics. It's fair to say it never sets at 0 degrees anyway. So what does this mean? Well, if the sun turns out to be 1,000 miles high or less, then we only need to account for a 9-degree or less elevation angle at sunset. This is pretty ideal. The sun may even be less than 500 miles high. When you start to seriously study chemistry, our atmosphere, electromagnetism, refraction, and optics, an unlimited amount of doors will open for you. So the different ideas work together perfectly, and you can see how important it will be for people to continue research. And then they start to say things about the thermosphere like that it reaches 2,700 degrees, but then they make excuses as to why that won't melt the ISS. Brian Mullen had a very good video on the subject. If they claim to not be melted at that height, then how did they measure the temperature to begin with? And whatever is making the particles hotter, shouldn't that also be heating the ship? One possible explanation for the temperature increase in space is simple. They're close to the sun. We might see it go from extreme heat to extreme cold. All kinds of elements could be generated up there, maybe highly refractive elements, further layering our atmosphere. After all, if the Earth is flat, why should we assume the sun and moon are flying through a vacuum? Especially if we know that NASA is feeding everyone false information. It's much more believable that the sun and moon are something so unbelievably awesome that it would humble and amaze all of us. Also, light changes speed in water and gas. This is very important, and when you realize this, you will be amazed at how much modern religious scientism falls apart. Light can slow down anywhere from 3/4 to 1/3 of its speed through water and glass, and using a crystal you can even trap light. By use of a Bose-Einstein condensate, Danish physicist Lene Vestergaard Hau at Harvard University succeeded in slowing a beam of light to about 17 meters per second. Okay, so why does this matter? Well, there are many things you can do with light. You can refract it, changing its direction, you can diffract it, you can separate the waves, and sometimes isolate color frequencies, like Royal Raymond Rife did to analyze bacteria without harming it with the world's most powerful cellular microscope that he made. Or you can reflect it. So this can be an important problem because modern scientists base all of their measurements on c, the speed of light, which they calculate in air. But remember, air is filled with at least 30% humidity and tons of other chemicals that refract light. It's not even close to being transparent. There is so much air pressure that it can cause planes to rip apart if they fly too fast at low altitude. They never measure this speed on Earth in a vacuum chamber. Their official number for c is based on experiments done in lower atmosphere, which we can prove because people actually measure this and post those videos to YouTube. They might use an oscilloscope and a mirror, for example. Let's also consider the margin of error in their measurements and in their equipment. Now, if you are not measuring c in a vacuum, then how can you know its true speed? It clearly moves slower in air, so the speed of light must be wrong, but how much is debatable. However, if you suck the air out of a train, it will crush like a tin can. Sending lasers from Earth to be refracted back won't work either, because it still needs to travel through the atmosphere. So who can measure light in a vacuum? It's possible that it's almost infinitely faster. So why does this matter? Because it debunks the speed of light and brings relativity into serious question. But don't take my word for it. Let's look at this video by Norman Wildberger again. He does an absolutely brilliant job showing you mathematically why GPS would not possibly work without relativity. The math is absolutely beautiful. He brings up the Michelson-Morley experiment, which proves the Earth wasn't spinning, because no matter what direction you measure light, the result is the same, even in the direction of the alleged spin. The globe Earth was basically screwed by the experiment. Norman starts talking about relativity in GPS at around 20 minutes. So the problem with satellites is they have to use atomic clocks and measure time extremely accurately. They say many satellites are 23,000 miles away, for example, or even more in some cases. So right off the bat, you know that anybody who thinks they have seen one has obviously had it confused with a weather balloon or something else. Nobody is going to be seeing anything 23,000 miles away. Second, the satellite somehow had to get past the blazing hot thermosphere, and third, why the hell would anyone send satellites 23,000 miles away when they can just use weather balloons or skywave or fiber optic cables or ground-based towers, which is exactly what they do. And of course we have no videos of the Earth spinning and no photos that aren't CGI composites. If those satellites were real, there would be thousands of videos of the Earth spinning and thousands of photos. Well, one thing that is certain is light can move longer distances vertically because there are less obstructions and it's moving through a less dense medium. Technology such as skywave, for example, has been around for a very long time, and it functions by reflecting waves off of the ionosphere. A similar effect can be achieved with balloons, sending signals from one to another. Now, Norman is a genius mathematician, and he explains that the results of GPS and its ability to triangulate would be off by milliseconds. Then he uses relativity in his math to fix the problem. So he's forced to use relativity here. Relativity says that time slows down the faster you approach the speed of light, but only for you, the time traveler. So because the Michelson-Morley experiment didn't fit the globe model, and because their fake satellites would have latency, they decided that everything travels through time. First of all, Norman makes some assumptions. First, he assumes that the speed of light is correct. But we already know that light was measured in the atmosphere and not a vacuum, so it can't be perfectly accurate. So his first assumption is based on an incorrect number. Next, he assumes the government is telling the truth and that there are satellites 23,000 miles away. Now you tell me, what is more logical? Is it more logical that light travels through time, or that the speed of light was wrong? Is it more logical that light travels through time, or the government lied about satellites? Does light travel through time, or does the Earth simply not spin? Does light travel through time, or are satellites actually just balloons and skywave and ground-based technology? Tesla was one of the greatest minds in history. He discovered alternating current. It says he discovered the radio before Marconi. He invented more things than almost anybody of his time. He was literally the father of all of our modern technology. And he didn't believe in relativity. He also did not believe in the atom molecule. And he believed that electrons were physically impossible. Look at some of these quotes by Tesla. He was obviously a huge fan of the geocentric model. Tesla believed in the scientific method. He did not agree with the idea that you make up a theory to explain a phenomenon. That is the reverse of the scientific method. It borders on religious dogma. Tesla would lament that science moved away from experimentation and into math and conjecture. But Einstein didn't care. He's famous for saying, if the theory does not fit the facts, change the facts. In other words, what he's basically saying is, I'm right, and if you don't agree, I change the laws of your reality.
We are men of action. Lies do not become us. Well spoken, sir.
Relativity is just as nonsensical as his idea of gravity bending space. They always show you space bending on one plane, but if gravity bent space, it'd have to bend it in all three dimensions on all planes simultaneously, which is basically the same as saying nothing. And they made Einstein the man of the century instead of Nikola Tesla or Mahatma Gandhi or somebody else. Where Tesla gave us the modern world, Einstein gave us mathematical excuses. Also, if the speed of light is wrong, then light years are wrong, and so is every calculation that space agencies do. Stellar parallax was in constant dispute in the early 1900s. If you can't accurately determine the exact angle of refracted light, then why on earth would you think you can determine the parallax of a star? Well, there is no stellar parallax, and it is much more logical to assume the stars go around us. Otherwise, the stars would move in synchronicity and force scientists to assume the galaxy is flat. Scientists also assume that the solar system is flat. But how can the solar system or galaxy be flat? That is a statistical impossibility with no regard for three dimensions. Believing this is almost a religious belief. Why do people agree with this? So who's the bigger flat earther, us or them? I have an idea. Don't assume the galaxy with its alleged zillions of stars is on a flat plane, and instead simply assume the Earth is flat, exactly as it appears. They never even give a satisfactory reason as to how they think the solar system became flat in three dimensions. I doubt you will even find a working computer model for that theory, although I'm sure somebody somewhere has made us a pretty animation. Most modern theories are hardly ever questioned. If the subject of stars interests you, I highly recommend you investigate this further. So what about a theodolite for measuring angles? Well, surveyors use them all the time. They are, however, not very useful for extremely long distances. Not to mention, as distances increase, so does your margin of error. So another question about the sun is, if you use a solar filter, then the sun will not shrink in diameter. Well, first of all, there is very little footage, if any, of the sun for 24 hours through a solar filter sunrise to sunset. Also, most of the footage zooms in on the sun. This makes a continuous shot a lot harder. However, thanks again to Phuket World, who shot the sun through a solar filter, and he posted his results, and we do see a diameter change. However, round Earth believers give us their videos showing the size not changing. However, most of these videos are very short and thus inconclusive. So which one is it? I would like to see the Flat Earth researchers perform a 24-hour time-lapse with a solar filter and no zooming so the shot is continuous. Also, the atmosphere refracts the sun and it increases the diameter of it as it passes through air. The further the sun, the more air it'll pass through, and the more it won't shrink as much as we expect it to. This was explained in my first video. Also, it depends completely on the light source and the lens of the light source. For example, when you use a projector, the image actually gets bigger as you get further away from the projection. By the way, in my first video, a few people wanted to know how I can prove that we were walking backwards. Well, you see the diameter of the light shrink, and in one shot you can see the light overhead. The reason it descends so fast is because we sped up the footage 300%. In fact, you can tell a lot of the clips that we used were sped up to fit the video within the audio and get it within 10 minutes. We walk backwards from the table in the room to the end, which is about 15 feet away. Plus, you can do it yourself. Do it with 2 cameras if you like. Do it with the lights on even. The results will be the same. In order to set it up, just use transparent sheets, cut them into different heights, and stack them on top of each other. The more sheets for each layer of atmosphere, the denser that layer of air. You can also experiment with different gels and simulate different elements. Some people ask, why does the sun approach left to right or right to left in different hemispheres? Well, obviously that depends entirely on which way you are facing and if you are north or south of the sun. I've noticed that people use these videos where they show a stick and shadow going around a little piece of paper with north marked on it. But this is clearly wrong, because if you are south of the equator, the sun will be approaching from the east, which will be on your right-hand side if you're facing north, and it will cast a southerly shadow on the stick. As it moves from right to left, the shadow will appear to move counterclockwise. If you perform the same stick and shadow experiment north of the sun, the shadow will move in the other direction. Of course, the sun can't change from clockwise to counterclockwise. The sun's path at the equator is never straight up and down. On a flat Earth at 90 degrees under the sun should always swing in slightly northernly. Also, the equator is not possible in a round Earth model. The equator's position in both models depends entirely on the season. In a flat Earth, the sun traces different circles spiraling outwards for the seasons. In a round Earth, you can't have an equator because of axial tilt. This causes the Earth to be on one side of the sun 6 months later. The side of the Earth that was tilted towards is now tilted a ways. That's their explanation for seasons, but it doesn't actually make any sense. Look what would happen to the South Pole. If the South Pole was ever exposed to the sun like that, the temperature would rise dramatically. But if you compare North and South Pole temperatures, the South Pole is always a lot colder. So which model better explains seasons? Easy, the flat Earth model. The flat Earth model has the South Pole along a much larger line and further from the sun. Also, equatorial countries keep a very consistent temperature year-round, and northern cities get unbelievably hot, like Vegas and Mexicali, despite being slightly above the equator. This is because in the flat Earth model, the sun spirals inwards and outwards depending on the season. In the flat Earth model, the sun spirals would average in the center of the equatorial line, giving a pretty consistent temperature, but it would move slightly above and below it to account for seasons and would still be distant enough to set from everything. We can also measure 10,000 kilometers from every single point from where it sets. Both models explain varying daylight time, but the round Earth suffers from the fact that the Earth is on the other side 6 months later, forcing them to prove the impossible. Why isn't day and night not flipped 6 months later? So the flat Earth is a lot more modest in daylight times. If the sun is further south, it circuits near the southern hemisphere countries for much longer. Also, the sun's speed in the flat Earth increases during that time. Then it spirals inwards into a smaller circle. Some people have theorized about a dome, and although that's a very interesting idea, it's a little bit beyond the scope of this video. There are many theories out there. Some think there is more land, some think there is a dome. What is absolutely certain is we are not on a spinning ball. Also, crepuscular rays is strong evidence that the sun is a lot closer. A great video by P-Brain was done on the subject, where he shows how the light angles would come in. Now, you might say that this is due to perspective, but the problem is crepuscular rays are pretty localized. There are also hotspots from the sun, and the angles of crepuscular rays are extremely sharp. The sun appears closer because it is. Finally, we come to one of my favorite subjects, and that is the subject of Fata Morgana. Fata Morgana is a complex form of superior mirage that is seen in the narrow band right above the horizon. This optical phenomenon actually dramatically favors the flat Earth. In my previous video, I explained how the waterline can appear slightly higher due to the tremendous amount of water particles near the water's surface, which can form an inferior and superior mirage. Fata Morgana is usually layered and usually inverted, or both inverted and straight. Well, when you zoom in on the horizon, you are only looking at this extremely thin line of the horizon. It becomes pretty self-evident that after 40 miles, strange things can start to happen with compounded air. What do you notice about every mirage that you see? Well, first of all, they're completely awesome. They're also pretty common over water and over the hot desert or in extremely cold climates. This mirage here is awesome. Look at how it looks like a flying ice wall. One thing that most mirages have in common is they are wavy, with fractals, and sometimes they look ghostly looking. Compared to the time-lapse of the Chicago skyline, there is absolutely no way this is a mirage. It looks nothing like the images you just saw. The entire city is intact, and there's no wavy lines or inversion layers. Also, things that you can see within 10 miles away at sea level, like boats, islands, and other shorelines and so forth, should be more than 6 stories below your line of sight. These are daily occurrences. Go to the beach and prove it to yourself. And remember, it squares with each mile on a curve, so each mile becomes more and more impossible to explain on a ball and easier to explain on a flat plane. We can even see some things up to 100 miles away on a day with good clarity. So we can obviously tell the difference between what is and what is not a mirage. Look at this crazy mirage over the desert road. It looks like the road is a pool of water and the car drives into it and almost gets devoured by the light. Now, an inferior mirage usually causes the illusion to appear below, and a superior mirage usually causes the illusion to appear above. The superior mirage is usually considered a little more stable because cold air stays below on the horizon line. However, any air current or heat on the water from the sun will cause the heat to mix with it, and that's why they're extremely rare. Flat earthers avoid the subjects of mirage and refraction, but this should be their favorite subject. It usually works in their favor. Superior mirages are more common in northern climates over ice because there the air is cold enough to make the effect more probable. If inferior mirages and fata morgana are more common, then we can prove that the majority of mirages are actually unstable. This type of mirage is commonplace in the desert and over lakes. Inferior mirages are not stable. They will constantly shift and change forms. We have been told that mirages are more common near the horizon line. So if people are saying that the Chicago skyline is a mirage, then they must give examples of inverted cities and prove that this is a common and everyday occurrence. Also, because air density forms a gradient, it's unclear that a superior mirage would be able to happen to an entire city over a lake. And also, you can see the Chicago skyline any day you desire. The visibility in the time-lapse of the skyline is obviously due to clarity. When the clouds clear, it's visible. Also, this is just one of tens of thousands of examples. Any day you can visit the Bolivian salt flats or see mountain ranges or cities for miles. You can see other islands and boats on a daily basis. So if inferior mirages are more common, would it not be more reasonable to assume that it has an effect on the waterline, normally causing the waterline to appear slightly higher? And also consider the effect that our atmosphere has on light. When you study it, you will be amazed and your eyes will open and you will know the truth. So hopefully this video has been helpful. I'm going to attach a frequently asked questions to this, so researchers can make their own videos based on what they have learned here. This video is meant to be a very high-level analysis of the sun, angles, refractions, optics, and other things that have not been covered enough in the Flat Earth movement. It's an extremely advanced course in optics and light.
Wikipedia actually defines atmospheric refraction as the deviation of light or other electromagnetic waves from a straight line as it passes through the atmosphere due to the variation in air density as a function of altitude. So it's saying as the air it's closer to the ground, it's more dense. So atmospheric refraction near the ground produces mirages and can make distant objects appear to shimmer or ripple and appear elevated or lowered, stretched or shortened with no mirage involved. So now let's take a look at the sun. Is this not what we see? Can we not see ripples in the setting or rising sun? I think we are clearly seeing atmospheric refraction here. Could we also conclude then that due to this light refraction, the sun appears to be lower than it actually is, as previously stated? Now people will argue that the flat earth theory must be wrong because if the sun were circling overhead, then it must get smaller and smaller until it ultimately disappears. This is essentially what happens though. But as the sun approaches this vanishing point, the light begins to distort and refract, making it appear to sink below the horizon. In some parts of the earth though, this refraction does not take place. Couldn't the phenomenon of the sun turning distorted and rippled, appearing to sink and changing darker color, happen on a globe too? I mean, after all, we are rotating away from the sun, which increases the distance the light is traveling to us, right? That can account for the light refraction, right? On a globe Earth then, you would need to justify that the sun is not actually moving further away from the observer, but the observer is rotating away from the sun, which we are in that model. But how far are we going? The Earth is rotating at about 1,675 kilometers an hour, 1675. Depends on where you are though, it's faster toward the equator. Now to make the math work, we would need to convert those kilometers to miles. This would be about 1,041 miles per hour. It's pretty fast. It's fast as shit. Now from 12 p.m. to 6 p.m., approximately when the sun sets, you would go 6 times 1041 miles, or about 6,246 miles, not accounting for the curvature though. Just to make the math simple, that's about how far you would go. So that's a long way, right? Explains the light refraction, changing color, mirage? And I don't think so. Not at all, actually. You need to consider the relative distance that you are rotating away from the sun, out of the whole distance. The sun is 93 million miles away from the Earth. Relatively, we are not moving far away from the sun at all in this time period from 12 to 6. In fact, we moved 6,246 miles away from the sun out of the total 93 million. So doing the math, the distance we traveled divided by the total distance is 0.0006716. Or 0.0672% rounded. So objects look distorted and refracted as they get further away. Good, I get that. But you're trying to tell me that an increase or decrease in distance that light travels of a measly 0.062% is going to cause the sun from looking white in a perfect sphere to dark orange, rippling, and misshapen? On the flat Earth model, these calculations are not exact, but the sun could easily go from the estimated 3,000 miles above your head at noon to 5,000 miles away from you at sunset, which is almost double the distance out of the total distance. That's almost a 50% increase, about 744 times that of 0.0672. This much larger increase or decrease in distance could much more easily explain the phenomenon of light refraction regarding the sun and the distortedness and change in color.
So, the process of testing claims, the world is flat, the world is round, is what we call science.
We did this observation at nighttime to see if we could see the tower because it's illuminated. Here's the tower from 30 miles away, and if I zoom in a little bit, the ballers argue that the evidence is inconclusive because we have on one side the tower, we have 2 dots, we have what is the roller coaster, and we have this glitter ball, which was hotly debated. Okay, now what we're supposed to see at this distance is this is, where's it gone? I'm looking for, it's been a while. There we go. This is what we're supposed to see according to Midwest magic refraction stuff. Oops. We're meant to see that. This is all that we should see of the Blackpool Tower, but when we actually go there, this is what we see. So there's the whole tower. Now, what I'm going to do with you to put this into perspective for those of you that are not familiar, I will, oops, that's a zoomed in picture. I will show you the shoreline, basically kind of similar to what the picture shows, just so that you can see it. All right, so this is the line of sight that we're on. Okay, there's the tower in the background. There's the roller coaster in the foreground. And if I zoom into the line of sight, this thing here is called the adrenaline rush. And it's either this post on this post or maybe this post. But in any event, these dots that are here is evidenced in these two dots here. So don't forget, Magic Mix said that the horizon is supposed to be up here somewhere, but we're seeing all down here. So these are like 100 feet tall. Standard refraction is based on 7/6 of the radius of the Earth, all right? And then underneath he says standard refraction is an approximation of the refraction expected under standard atmospheric conditions. And when you click the link, it don't talk about 7/6 of the circumference of the Earth. It talks about the continue. Here we go.
Snell's law, right? Isn't that Snell's law?
No, it doesn't even talk about Snell's. It doesn't even apply. This is why this is a problem, because in the explanation for, I need to actually go to the link. Give me a sec while I pull up the link, because I can't remember where I had it. So give me a sec.
While you do that, I'm going to do a quick link to the audience, if you don't mind. So,
okay, so just to conclude my point, and then you can come back to me. Standard refraction is based on 7/6 of the radius of the Earth, and he says it's based on the approximation of the refraction expected under standard atmospheric conditions. But when you click into this, the calculation is there you go. The ISA mathematical model divides the atmosphere into layers with an assumed linear distribution of absolute temperature against geopotential altitude. The other two values, P and D, or pressure and density, are computed by simultaneously solving the equations. Okay, vertical pressure variation and an ideal gas law in molar form. But it doesn't mention anything about 7/6 of the radius of the Earth. And also, it doesn't mention anything about the application of Snell's law. Now, why is that?
It's a good question.
Yeah, so let's get Curve to answer, because Curve is the one that's asserting that standard refraction is a thing. I've just shown you that it's based on a 7/6 of the radius calculation, but it's based on the standard atmospheric conditions, which don't account for a 7/6 of the radius of the Earth, but also don't account for the application of Snell's law. But you guys include Snell's law. So why is that?
How do you think the calculation is done, Riley?
Well, it shows you in here. If you read what it says the ISA mathematical model divides the atmosphere into layers with an assumed, that's a keyword, linear distribution of absolute temperature against geopotential altitude. The other two values, pressure and density, are computed by simultaneously solving the equations resulting from the vertical pressure variation and the ideal gas law. Doesn't mention Snell's law, and nowhere in this article is Snell's law mentioned. So my question is, why would you go into Snell's law when it's not based on this, which is what it's supposed to be, the standard atmospheric conditions? And why does the standard atmospheric conditions not mention 7/6 of the radius of the Earth when it talks about the continuous simultaneous solving of the equation? It doesn't mention this at all. So this is bunkum, unless you could explain for why it should be there. And also, why is Snell's law not in the explanation for standard atmospheric conditions, of which this is based on? Can you tell me why Snell's law is accounted for when it isn't accounted for in that article either? There's no mention of Snell's law in here. Do you understand what a simultaneous solving of an equation gives you?
Oh, God. Riley.
Answer the question.
You keep on doing it.
So what's the end then? What's making the equation end?
There is no end to it. It's the variation of the vertical pressure variation with the.
I know there's no end. That's what I want him to say. That what's making the end? Because you put in a variable, and without the variable, that's the only thing that makes it end.
Because if it was the continuous solving of the equation, according to what he says, which is the 7/6, that would mean that we would see the building in the background shrinking and stretching.
7/6 is a standard approximation.
Yeah, but it's based on the atmospheric conditions here, because it says it is. Now, if you do the continuous solving of the equation that's here, what that means is that the building that you're looking at should be falling behind the curve of the Earth, bringing back up, falling behind the curve of the Earth, bringing back up. But that's not what we see, is it?
It does when the conditions change.
Yeah, but it's based on the atmospheric conditions here, because it says it is. Now, if you do the continuous solving of the equation that's here, what that means is that the building that you're looking at should be falling behind the curve of the Earth, bringing back up, falling behind the curve of the Earth, bringing back up. But that's not what we see, is it?
It does when the conditions change.
Yeah, but no.
Changing conditions cause exactly that appearance.
All
up
right,
and
so
down.
Let's go with the skunk bay footage and let's see what actually we see when we see over time lapse, because it's the only example that I know where there's time lapse done of distance observations. I don't think during.
So he's trying to say that during the time of the observation, it's going to grow a hump, then it's going to curve.
That's what the continuous
fraction's going to a fraction's going to appear. That's what he's saying.
Well, that's what
curve.
That's what that mathematics is saying. Yes.
Over time with changing conditions, yes, the appearance changes.
Okay, so let's see.
So what is over time? How long is over time going to take, though?
It depends on how long it takes for the conditions to change significantly. And the appearance will change in accordance with the degree of change.
Let's show an example where we've got time lapse of a horizon and see what the effect of it actually is, because we can see this. There we go. This is it here. Okay, so we're at 9 a.m. in the morning. There's not a lot of atmospherics going on. You can just see a little bit of a shimmer beginning to come in. As we get up towards midday, we're getting to say nearly 10 o'clock now, and you're beginning to see the continuous solving of that pressure and the air density equation that we were just talking about. This is what we're actually seeing, and it shimmers. Now, notice this background.
The mountain in the background, is it breathing?
Now, is it falling behind the curve of the Earth?
Is it breathing?
Hang on.
Is it breathing? The top of it seems to be going up and down. It's like it's undulating or something. Is that Gaia breathing?
Is it stretching and shrinking, or is it falling behind the curve and coming back up again?
Going up and down. You can see it. It's not falling behind the curve. You can see it. That's not the claim. Don't be a moron.
No, but the claim is
I'm talking about it going up and down, just like we claim.
Yeah, but it's based on the atmospheric conditions here, because it says it is. Now, if you do the continuous solving of the equation that's here, what that means is that the building that you're looking at should be falling behind the curve of the Earth, bringing back up, falling behind the curve of the Earth, bringing back up. But that's not what we see, is it?
It does when the conditions change. You've got tides going on here.
No, you're misunderstanding the point. Let's go back to the point because you've missed it. Let's go back to this.
No, I haven't missed anything, Riley. You're missing it all.
No. It says it's the continuous. The other two pressure values are computed by simultaneously solving the equations from the vertical pressure variation and the ideal gas law. Okay, you're seeing the evidence here. This is what it happened. This is what. This is what time lapse shows you. This is what the effect of the horizon does. Now, your position is that it falls behind the curve of the Earth. My position is that it stretches and shrinks consistent with what the explanation shows you. Also, my position is that Snell's law doesn't apply because it doesn't say that it does, and that the 7/6 application of the radius of the Earth doesn't apply because it doesn't say it does.
Dude, do you not see physical objects on land moving up and down in the image?
Yeah, but they're stretching and shrinking like a continuous solving of the pressure variance.
And you see things moving. Do you think they're really moving, or do you think that's an illusion caused by the refraction?
Now
come on, genius.
It's the second one, obviously, but caused by the refraction is what's happening. Is it the stretching and shrinking, the vertical variation, or are you trying to tell me that that's going further away from us and dropping behind the curve of the Earth, just like the building, the mountain in the background? Come on,
simpleton. It's an appearance,
right?
Based on the
which answer is it though?
So you can't. Yeah, exactly. You can't have
it two ways. If you don't know the answer I just gave, please refrain from asking such simple questions.
Right, so basically your position is that the mountain in the background is falling behind the curve of the Earth and flicking back up again, right?
I never said that, Riley. No.
Yeah, but it's based on the atmospheric conditions here, because it says it is. Now, if you do the continuous solving of the equation that's here, what that means is that the building that you're looking at should be falling behind the curve of the Earth, bringing back up, falling behind the curve of the Earth, bringing back up. But that's not what we see, is it?
It does when the conditions change.
Well, that's in that case, you have to accept that it's refraction exactly the way we see it here, stretching and shrinking.
You're either dead or you're alive. There's no in between.
Yeah. So at 30 miles, and we know that that whole tower was meant to be obscured behind the curvature of the Earth, and we saw the whole thing. And you're saying that that's to do with refraction, but I'm saying that the effects of refraction are actually the distortion of what we see, not stretching behind the curve of the Earth. It's stretching and shrinking what we see, which is exactly what you're seeing evidenced here. I understand that what's described there is not the same as what's shown here, because that's an arc mathematics.
You're either dead or you're alive. There's no in between.
Yeah. So at 30 miles, and we know that that whole tower was meant to be obscured behind the curvature of the Earth, and we saw the whole thing. And you're saying that that's to do with refraction, but I'm saying that the effects of refraction are actually the distortion of what we see, not stretching behind the curve of the Earth. It's stretching and shrinking what we see, which is exactly what you're seeing evidenced here.
You're either dead or you're alive. There's no in between.
I understand that what's described there is not the same as what's shown here, because that's an arc mathematics. That's not mentioned. And Snell's law isn't mentioned neither.
Standard refraction of 7.6.
Why should it mention Snell's law? Like, why do you think it should mention Snell's law?
Because they cite Ball Earthers cite Snell's law for this apparent 7.6 of the curvature of the Earth.
Oh my God!
That's included in.
I just felt like people could have said that the Earth was the shape of a star, and everybody would have believed it.
No, only people that believe NASA. Only people like Brenda and Curved would believe it.
So it says the standard refraction of 7.6.
But yeah,
why do you make such stupid claims, Riley? I'm not on.
I don't think he doesn't know what he's talking about.
These are not my claims. These are your claims.
No, why are you trying to link me with NASA, Riley? Why are you so desperate? You don't know a thing about me. You don't know my stance on NASA.
No, but what I do know
shit about NASA.
He knows flat earthers won't be able to understand that he doesn't know what he's talking about, so he just sits here and makes stuff up.
Yeah.
You don't know what he's talking about.
Because
right, no swearing. Right, I'm going to turn you all down and just say a quick hello.
Every time when a flat earther asks something, he's not making sense or he's ridiculed. Though.
No, he start moonwalking.
We just want to need to know basis.
Ridiculed because he's trying to have threesomes with.
Now that we've gone into ad hom attacks, that basically means that you've both conceded.
That's not ad hom, Riley. Yeah, you tried to have a threesome, and you're not a real like. How is that an ad hom? So you're not genuine.
You're either dead or you're alive. There's no in between.
So you have to take temperature, relative humidity, dew point temperature, how much moisture is in the air versus how much the air can hold. All these are different factors in determining the air pressure and more. There's other things too. However, the bottom line is just like with blood pressure, all you need to know what the millibars are to tell how much refraction you're going to have. You don't have to, it doesn't matter what the temperature is, because whether it's 10% salt or 70% salt, they both result in the same number. It's all mixed together to come up with the main number. All right, 1,013 millibars equals 1,013 millibars, which is one standard pressure. You will have the exact same refraction at 70 degrees versus, let's say, 90 degrees. Jesse's example. Why? Because the main thing we're comparing is the same. All right, let's move on. This is a surface weather analysis taken at 15Z or 1500 GMT, Thursday, June 8th, 2017. I want to show you some scale here. I lived in Maryland, so this is the most you can zoom this map. So I'm going to go with top zoom. You see this little circle here, or where my cursor is, and this little square here? This is Baltimore, Maryland. This is Washington, D.C. This little teeny space right here is 40 miles apart. Roughly the same distance where Tony's doing his experiments over in the UK. All right? Barely a difference. Now, I'm going to pick something that's not so conglomerated together there. Let's pick the middle of the country. I'm going to pick Missouri. Why? Because there's a high pressure here that's going to take you, no matter what direction, away from this high towards lower pressure. Now, we could go the other way, low towards high. It doesn't matter. It's just a matter of what, are you looking away from the high pressure or towards the high pressure? Now, let me just give you one quick overview of one station here so you can see how this works. See this little line to the bottom? Okay, this is about 190 degrees. This is from the south-southwest winds at 5 miles per hour. The temperature is 72 degrees Fahrenheit. The dew point temperature is 55 degrees Fahrenheit. The barometric pressure in millibars is 1,017.7. The 10 is dropped off. All right, 10 is dropped off. Now, if this started with a 9, it would be 990 some millibars or whatever. So, even, let me take it a very extreme. We're going from Missouri way out here. This is, I don't know, 700, 800 miles. Let's just use this one, 140. This is a 1014 millibars, 1017. 3 millibars, 3.7 millibars difference in all this different. 3.7 millibars went from the top of the atmosphere all the way down to the surface. 1013, very close to where this is here, is your standard atmospheric pressure. 1013 millibars from zero gives you that tiny little refraction. And here we go, 800 miles, 1,000 miles, whatever this happens to be. 500 miles, I don't know. I don't want people to hit me on the miles because it's stupid. But you're never going to compare something 500 miles apart, are you? No, it's too far. You have 1,014 millibars versus 1,017.7. 3.7 stinking millibars and all that distance. In this case, the temperature happens to be the same, 72 degrees of both. But let me show you something. In the same state, this is probably 75 miles apart, these two reporting stations, just roughly 75 miles to say. You have a temperature of 72 degrees here and a temperature of 74. A lot of people say, well, see, there's a 2-degree difference, Rich. You're going to have refraction. No. They both have 1,017.7 millibars. What does that mean? The density of the air, for all intents and purposes, is the same at both. Now, there are other factors that could be here. For example, it's a little bit drier here, so the refractive index might change by 1/10 trillionths, I don't know, of a point. But for the most part, it's all wrapped up in this number right here. You don't have to worry about the temperature. Now, let's go through the whole state here. 73 degrees, 75, that's the high so far. 75 in another state. 74, 72, 69. Oh, 69, we got a 69. All right, in one state, from here, where's the 75 to here? That's 150, 200 miles at least. 200 miles is called. 200 miles, we have a 6-degree difference in temperature. 6 stinking degrees. What's the difference in the density of the air? This is 1,017.3 millibars. This is 1,018.1. Less than 1 millibar difference. Or I'm sorry, less than 2 millibars difference. 1.8 millibars difference, 1.8, when we get this tiny refractive index of 1.0 to 1.00027 from 0 millibars to 1,013 millibars. Incredible. So you tell me how far, we're generally talking 35 miles, this kind of distance here in Maryland, okay, this to this. This is what Tony's doing, this to this. And you're talking about refraction, raising things up, like somebody said it was raising up 400 feet or something. That's just simply a please. You don't understand what's going on. This is what you look at. Forget about temperature. Now, if you have a 72 degree temperature, let's say it's 6 feet, when you're observing at 6 feet, and by the way, Tony was like 10 inches above sea level, so that's not even the case. But let's say you had 72 degrees, and on the surface where you're looking 35 miles away, it's 90 degrees because it happens to be where a street is. And it's 90 degrees and you're looking through it. You're going to have distortion at the bottom. It won't raise it up. It will distort it like we saw in the sun. So hopefully this makes the point. Now what he's got here, he's got a green line. All right, this is the path. Once you get here, this person can no longer see any farther. All right. Now what he's showing here is the light bending down. Suddenly it starts right where the point where this observer can't see anymore. Why does it start here? I want to know that. Why does it start here? It magically knows that this is the horizon, so it should start bending. What if the person's a little bit higher up and the horizon's farther out? Would it still bend there? See, these things are to me ridiculous. They're absolutely ridiculous. We're talking about distances of 35 miles. So, as you saw in the example on the weather map, at 35 miles, let's say we have a whole 2 millibars difference. That 1.00027, or 1.00027, that's correct. When you do the math on that, when you actually do the math, when you subtract the 1.6 degrees from with the resulting angle you get, it's what was it? It was like 3/1000ths of a degree. Now imagine you're here with a sextant and you're looking out. With a sextant, if you never use one, guys, you have degrees and then you have tenths of degrees. And if I remember correctly, I had a good one. You could go down to 100th of a degree. A very minute change would be 100th of a degree change in your sextant looking at something on the horizon or something in the distance, or measuring the height of the sky or of a celestial object in the sky over the horizon. You would drop the thing down and it would give you degrees. To center it more, you would go to the little adjustments that would be on the device. Again, it would go, if you have a good one, down to the 100th of a degree. And even that was very, very, very difficult to even know you were turning the dial, because it didn't change anything in your line of sight. Very, very little. You couldn't notice it. The eye couldn't pick it up. All right. We're talking about 3/1000ths of a degree. 3/1000ths of a degree. There's not even an optical instrument that I know of that a person could look through and adjust to something that's sensitive. And yet, that is what it would be, looking from a void in space down to 1,013.25 millibars. That would be your refractive constant. So we got to stop using things like X percent per unit of distance. As I showed before, distance doesn't matter. Once you change a medium from air to water, let's say, that is where you get your bending. It only happens once, and that's it. It doesn't continue. It doesn't get higher per unit of distance. If that was the case, the further you stood away from a glass with a spoon in it, the more it would bend. Or the more water you had between you and, like I said, if you had an aquarium that was 100 yards long and you stuck the equivalent, let's say you stuck a steel rod in the end of it and you're looking through 100 yards, the refractive index you would still use, it would still bend by whatever it was in water. I think water at 20 degrees Celsius, it bent 1.3 roughly, if my memory serves right. 1.3 would be the angle that you would get that would change. 1.3 degrees. That's the number. Where 1.3 is the number you use to multiply out to get the angle. That's going from something. That's from 1.00027 error to water at 20 degrees. Water is extremely dense, guys. Extremely. I don't even want to even guess how many millibars that would be if you could convert water into it. But as we know, water, even though it gets more dense as it goes down, all right, it's not, there's no by distance, unit of distance. That is a fallacy. You're going to have one abrupt change. In this case, they're going to say it's going to bring it up by a certain amount. In this case, it's like 3/100,000ths. Even if we're going from the void of space to one standard atmosphere, we're using 1/1000th of a standard atmosphere change in 35 miles. And that's being generous. The sun, the light from the sun. The light from the sun travels through layers of different temperature and density, refracting by refractive index percent. That has nothing to do with what we're talking about. Sunlight has nothing to do, or the heat or different layers of temperature the sunlight is going through has zero effect on what we're talking about. Zero effect. I'm sorry, it just doesn't. The light, whatever the source, the sun, a street light, whatever, a spotlight, whatever you want to use to illuminate this person all the way to the object, whatever it is, moonlight. Let's use moonlight because there's no different. Well, no, let's just use you just have street lights along the whole way. So the light has nothing to do, the temperature that the light's going through before it strikes the object has nothing to do with it. We're not talking about the vertical, we're talking about the horizontal. And I'm even giving it to you even though it's impossible. It's impossible for a person to only be able to see to here. And this is where the evidently just past where the person can see to is where the bending starts. Like I said, it's one bend. For it to raise it when you couldn't see it in the first place, and now you can. This is not the best medium to show you this. I'll show you that when I do the short version. But you can see this is totally crazy. Temperature has nothing to do with it, as long as you know what the millibars are. So Tony, next time you do it, find the nearest weather station to you, or just pick one. Let's say you're south of the tower. I think you're roughly south. Pick some weather station south of you, so you have even a more extreme, or you could take your own barometer there, but you have to know how to adjust it. If you want to know how to do that, let me know. So you can adjust it to sea level. But anyway, you're going to be at sea level, so that should be. But some barometers are off. You have to make an adjustment. So you take what you have there. You have an observer, let's say at the tower. Have them have a barometer at the same time. You, in fact, get two barometers, synchronize them. Take one where you are, one at the tower. Once the barometric pressure is confirmed at both, then you can do your little measurement, and then you can tell what the refraction is going to be. I can tell you one thing, it's such a small number, it's going to be less than 3/100,000ths of a degree on a sextant. Less than 3/100,000ths of a degree on a sextant. That is not going to raise this anything that you can see. So I'm going to end this here. Temperature makes nothing. Know what your air pressure is. That's your density. Standard air has a density of 1013.25 millibars. And standard water has a density of whatever it is. And the difference between the two, if the water is at 20 degrees Celsius, is going to give you a value of 1.3. We're talking a value of 1.00027 from void of space to the human on the surface. And it doesn't matter what the temperatures are in between, does it? No. As long as you're at standard atmospheric pressure. In any case, this person would be looking down always at the object on the horizon. They can't see past it. So I don't know how, if they can't see past it, light is going to raise it up and then let them see it. I just don't get that. Maybe I'm wrong. I'll think it over, guys. But this whole temperature thing and this traveling through a layer and reflect by the unit of distance it has no part of the equation. None. Unit of distance means nothing. It doesn't matter if you're, it doesn't matter. Unit of distance means nothing. What the pressure is here, the air density is here versus here, matters. And as we saw on the weather chart, you can have, let me see. Let's say you're here looking out towards this low. You're going from a higher amount of air pressure to lower. Let's say you're out here happening to look this way. You're going from lower to higher. It can work either way, guys. To assume that it's always going to raise something up is a fallacy. It just is, unless you want to say, well, you're always looking, Rich, through more and more atmospheric density as you go out in the distance. Well, what if you're looking at a low pressure, where low pressure is coming, and it's normally less when you're looking out that way? How much low pressure has to be there before it compensates for the amount of density it's looking through? But I'm even going to give you that. Like I said, 3/100,000ths of a degree on a sextant is looking from a void to the surface of the Earth. How much less when you're looking at something that's got the exact same freaking air pressure over 100 miles here, or whatever this is. Say it's 80 miles, 75 miles, I think is what I said. Even though it's 2 degrees warmer here, the only difference that's going to make is maybe you get a little wiggle on the horizon versus if it was exactly 72, but you're not even going to get that. So that'll end this, guys. I hope that answers the thing for you, Jesse. Hopefully it makes sense to you now. Okay, here's the initial one you sent me. I gave you everything in this. I said, okay, you know, this will bend up even though you can't see it. It's just, none of this makes sense. I'm sorry, guy, it just doesn't. There is no unit of distance in the calculation. It means nothing. And the sun going through different layers of hot and cold as it comes down means nothing. Absolutely zero. It's like, what was the lottery number yesterday? That'll change the refraction we see here. And of course it doesn't. So it's just as irrelevant as this stuff is. I had density altitude charts, pressure altitude charts. I'm just going to show you how looking over a long distance is nothing for refraction purposes, density purposes. You know, you have people that think they know what they don't know. This has been my thing, guys. From the age of 5 or 6, I've been into weather. I'm 56 years old. I did this as my profession. I understand this. Let's look at this glass of water. Less dense air, more dense water. The greater density water makes the spin bend which way? Down. More density makes it bend down. Now, I had all kind of things explaining this. I'm just going to try to make it as simple as possible. You're going to think I'm crazy, but moist air or air that's got rain in it is less dense than dry air. Look it up if you don't believe that. Please look it up. So if you're looking through if you have a whole bunch of moisture, it makes it less dense, right? Less dense does bend up, but you're not going to see the mountain in that situation. When you actually can see, when you can stand on, like we saw the 45 to 60 mile pictures from the shores of Lake Michigan, looking at Chicago, there's no rain in there. There's no fog. If there is, you can't see Chicago. So you're getting a more dense atmosphere. More dense is warmer, drier, higher barometric pressure, a lower dew point temperature. All these things come in. Dew point temperature it puts all the factors together. This is very important. I'm going to show you this in one swoop here, that when you look at something distant, okay, you cannot possibly look far enough and have that much of a difference where you're going to see any refraction. And I'll prove this to you in this video. I will prove it to you. It can be proven if you have a telescope. So, let's watch. Now we're going to take a look at 2 different things here, 2 different weather observations taken 1 minute apart. 11:54 Eastern for Crofton, Maryland. That's between Baltimore and Washington, D.C. And 11:53 p.m. Eastern Daylight Time for Hagerstown, Maryland. Hagerstown, Maryland is in a high plain type area, gently rolling hills. where you have very low mountain ranges just west of there. So if the Earth was flat, you could see from Crofton, Maryland, 70 miles away to Harrisburg. They're 70.7 miles away. 70.7 miles away. Don't believe me? Look it up. You can look up any of this stuff. And that is as the crow flies, not driving. Driving distance is about 86 miles. However, we have eastern deciduous forests on the east coast of the United States in Maryland. You cannot see more than a block in Crofton, Maryland West because there's trees everywhere. So, but what I want to point out is if you were looking from Hagerstown to Crofton or Crofton to Hagerstown, either way, it's 70 miles distance. Remember, most of the time we're talking 45 to 60 miles at most when we're talking about doing flat Earth calculations. Most of it is much, much, much closer than that, isn't it? I'm going to show you something here. Dew point temperature right here, 42 degrees Fahrenheit. This takes into account all the things that are necessary for refraction. All of the things necessary are included in the dew point. Why? Because the dew point is a calculation of many factors. The dew point will change with a change in barometric pressure, your relative humidity, wet bulb temperature, dry bulb temperature, density, altitude. I mean, all these things go into the dew point. So if you have big differences in dew point temperature, that's when you can have big differences in refraction. Why? Because dew point temperature is where dew will start to condense. The higher the dew point temperature, the more moisture there is in the air. The lower the dew point temperature, the less the moisture is in the air. So 70 miles away in weather, guys, unless you have a strong front in between the two cities that are 70 miles apart, let's say you have a cold front in between the two cities, first of all, you're not going to see, even if it was flat as hell on a very clear day, 70 miles, when you have a strong cold front, because you're going to have rain. And that's going to make the air less dense that you're looking through. That is when you could have refraction. On the clear, dry days, that's when it should, if anything, bend downwards. Dry makes you see, gives you the appearance of less, not more. We saw that with the glass. All right, dew point temperature at this time, remember they're only a minute apart, 42 degrees Fahrenheit. 41 degrees Fahrenheit. It's 1 degree Fahrenheit. For you, those of you over in Europe, that's about 0.6 degrees, 0.6 degrees Celsius. Look at these vapor pressures. I'm not going to go into them here. There's like 25 or 15 1,000ths of an inch of mercury different. There's virtually no difference. Look at the difference. Air density, okay, with water vapor 99%. Air density with water vapor 99%. We have 99% without water vapor, which is not true because every place has water vapor, would be 99% here. It would be 100% here. So the air density is virtually, I mean, they both have water in the air, obviously. Nobody has zero water in the air. They're both 99%. What does this say? The density in Hagerstown, Maryland, 70 miles to the west, is the exact same density of air of Crofton, Maryland, 70 miles to the east. It's actually to the southeast, to be exact. You're looking 70 miles, and there is absolutely, you pick up all the little towns in between that have weather stations. There will be no difference in the air density, in the water vapor in it. It just doesn't happen unless you have an extreme weather front. And in that case, you won't be able to see a far distance. In fact, the most extreme would be a warm front. And that's when you have low stratus and fog. That's when you can get those inversions that they claim to happen in Chicago. That's when those inversions are lifted like they showed, but what they didn't tell people was it was upside down, right? Yes. Of course, they made it flip upside down and then flip up again. But that would not happen 40 miles away. That could only happen when you have an extreme amount of difference in the density, such as fog or what's called, if you're familiar with the term clear air turbulence, it's where planes have turbulence, where there's no clouds. That is because they have there's near 100% humidity in the air, but for whatever reason, or even at 100% humidity, for whatever reason, a cloud has not formed. Maybe there's no cooling process, maybe there is no hydroscopic nuclei in the air. something is not presenting the cloud, but the aircraft still knows it, because when it hits dense air, what does it do? It drops. That's when you get turbulence. Have you noticed? You go through a cloud, boom, the cabin feels like it drops. It's because when it hits the cloud, okay, it's in less dense air. So the engines have a harder time pulling enough air through because it's less dense to keep it at the same altitude. Guys, this is my specialty. This is my thing. 70 miles apart. Got it? All right, let's go on. Now, let's go back to this real quick. Imagine it's a clear day, because it's the only time you're going to see a mountain 70 miles apart. You're in Crofton, Maryland here. This is Hagerstown. It's more like hills, not mountains there. There's about, I don't know, 500 or 600 feet difference between the altitudes of the two. So you're even looking up in the atmosphere through different layers. What was the difference in the dew point? What was the difference in the barometric pressure? Go back and look at those numbers. Minuscule. It's not enough. It wouldn't be enough if you had a laser pointer to see a 1/100th of an inch of refraction. And yet people want to throw, oh, well, okay, the refractive variant today is 22 feet. BS. Want the proof in the pudding? Here's the proof. Here's the proof. When you're looking from the surface, please get a, let me show a chart here. This is called a density altitude chart. That is the density of the air at particular altitudes. See the lines, how they slope up with altitude? This is your standard atmospheric pressure. This is where it normally is. This is the difference, okay? Well, this is the pressure altitude here. Let me show you that this goes into the density altitude, as you can see right here. This line going this way is the density altitude. Here's your figures over here at the 15,000 feet level, 10,000 feet, whatever. So you're going to have more refractive ability looking up than you are looking this way. Why? Because you're looking at a lot more than 70 miles in most cases. All right, you're looking all the way up to the stratosphere. Top of the atmosphere into the stratosphere. So you're going from a very dense surface all the way up to where there is no atmosphere when you're looking through a telescope looking at stars or whatever, correct? Absolutely. You're looking through much more telescope going up than when you do going this way. Now, let me explain a few things very quickly in case you didn't know it. You can get a telescope. You can put it on what's called an equatorial mount. You can put a drive on here and connect it to a computer that will drive this thing. You turn it on, it will recognize its latitude and longitude where the telescope is placed. You say, okay, I want to look at the moon. So it syncs up and it learns what your latitude, longitude, and your local time, and it pulls in the astronomical data that was written into this thing months, years, maybe even a decade earlier now. So this is how long this technology has been around. You can get drives from 10 years ago, 20 years ago, that still have data in it for now, that tell you when the sunrise will be, when the moon rise, when the stars, the planets, where they are in the sky. You can say, okay, show me Jupiter. This thing will say, all right, your latitude is 72.4 by 43.6, whatever, and your local time is this, and Jupiter should be right here right now, and the telescope will swing over and follow it the rest of the night. In fact, it'll follow it from the time it rises, gets overhead, and falls. So you're going to go through all different kind of conditions. When it's near the horizon, it's going to be looking at all the density this way of your atmosphere, and when it rises, it's going to be going through even more. You're going to be looking at even more, okay? Now, what factors do we have? You could have clouds, you could have clear air turbulence where there's more. You're going to have a lot of areas of more to less dense, even with no clouds. So that will change if it was going from clear to water. You would think it would be enough change in refraction so that the telescope wouldn't follow it, right? The telescope doesn't actually see it. It doesn't say, oh, there's Jupiter. I got it in the center. I'm going to track it now. No, no, no. It's all by the computer. And guess what, guys? No matter what your atmospheric conditions are, it's not enough to keep it from being in the center of your telescope. It might move it. You know, if you have really drastic differences between the surface and up high, you might get maybe, I don't know, maybe a quarter of an inch, what looks like a quarter of an inch movement from dead center in your telescope. Maybe, and you're looking at objects 250,000 to supposedly million miles away, and you're looking through all these different layers. You have clouds go by. When you look up at the sky, many people have seen this. You see the moon. You'll have sometimes puffy clouds go by, but you can still see the moon behind it. And you'll have high stratus clouds or high cirrus clouds move in front of the moon and things like that. It doesn't change the moon's position. It doesn't change the moon's position. It might make it brighter or less bright, but it doesn't change the moon's position. And you're changing drastically the amount of moisture you are looking through this whole layer of atmosphere when clouds go over it and not. Cirrus clouds you can see through. It doesn't change the position of the moon any. So you're going to tell me there's enough moisture looking east, west, north, south at an object on the horizon so that you have to calculate what refraction is? Come on, guys. It's bunk. This is proof. This telescope never fails. And it would fail. It might say, okay, if it's moist in the atmosphere, you might have to calculate, plus or minus whatever for refraction. You never have to do that. If it'll follow whatever you put in there, it'll follow it from the time it rises, goes overhead, and sets. It just will, guys. No errors. Years in advance programmed. And all this talk about the Earth shifting with every time there's a big earthquake, no, that's all bunk. We'll get into that another time. One last thing I want to cover because I saw it in the comments. Somebody was like, oops, you can't explain why you can see the sun at 270 degrees or 090 degrees on the equinox dates. Everybody on the Earth supposedly sees the sunrise at 090 degrees. I don't think that's true anymore. I think there's a couple degrees variation. I think we proved that now over the years. Doesn't matter. It is close. But here's the deal, guys. You can't explain it on a ball either. Oops. You cannot explain it on a ball either. There's no way you can have someone in North America, or let's say up near the North Pole, and someone down near the South Pole, and someone at the equator, and in between both the North and the South, all see the sun and the sunrise at 090 degrees on the equinox dates. It just doesn't work on either model. It does work, and it is in itself, this is the most underrated aspect of knowing that science is lying to us. And you can prove it yourself. Under certain conditions, if you're lucky, you can prove that science is lying to you. If you ever observe something called a rainbow, you can prove that science is lying. Because a rainbow, as science will tell you and has proven, requires 2 reflectors. If there's moisture between you and the rainbow, that's one reflector. What's the other? Between you and the sun. So we do not see the sun directly. That's what explains why everybody sees it at the same. I've got videos on this. I don't have time to go into it here. But that's why everybody sees the sun from the same angle on the equinox dates. It's because we are seeing a reflection. And I demonstrated that. We're looking like through a glass at it. Very easy to explain. And by the way, guys, the globe Earth people have this thing where if you can't explain something that doesn't exist, your whole theory is wrong. Guys, ours is no theory. They have no proof. None. Zero. Zip. Nada. None. There is no proof of a ball. Where is it? Where's the proof of any curvature? Where's the proof of any movement? We have scientific experiments show no movement of the Earth. Don't get tripped up, guys. This stuff, looking through all this, is your proof. Look up at the moon. Do you see it change position? When air is constantly going by that's more moist and less moist through the whole night? No, you don't see it variate at all, do you? It's all a lie. And that's much more than you would ever look near the surface of the Earth to find something. You're looking through much more of a density gradient and much more variation in between. You can have inversions. You can have all kind of crap going on here. We use our brain. We always get it right. This is an Olympic pool. And look at it. This is where it's the same level all the way down. The water's not moving, so we have no distortions at all. Look how everything is just beautiful from one end to the other. From the top to the bottom, there's almost no pressure up here. You're near the bottom looking up at a much less dense area up here. Do you see these things being distorted at all? Do you see these lines being distorted? No, there's no distortion. Why? Because when you're in the same medium, even when it's something as dense as water, that's the most dense any humans are going to be in, isn't it? I mean, unless you bury yourself in dirt in which you can't see anything. Come on, let's get real. This is the most dense we're ever going to be in, is this right here. Much more dense than the air, much more change from the bottom of the pool, or let's say this is the middle of the pool where the picture's taken, to the top to the bottom. We have no distortion, do we? Nice parallel lines all the way through. No distortion. Now, many people have experienced the following. Now, hopefully most of you have experienced this. I don't know if you have or not. If you haven't, talk to somebody who has. They will tell you I am correct. Imagine you're underwater here, swimming up to here, and you want to grab the handle. And you're under the water, and you look up, and you try to grab, let's say, this area right here, or this area right here, outside of the water. You're still under the water. You try to grab here. You try to reach out far enough to grab this part of the steps to pull yourself out. Guess what? Chances are you're going to miss. You reach and it's not there. Why? Because you are looking from inside the medium to outside the medium, and you get the distortion. You get a positive distortion because you're going from a thicker to a thinner. So it actually raises this up. Your hand will actually, instead of grabbing right here, will grab over here or too low. That's going from one medium to the next. But when you're going from air to air, looking from wherever you are to a mountain, let's say 100 miles away, you're in the same medium. There is no refractive index to use. Now, if you want to know how much it's going to bend from you looking underneath the water, how far is this going to be bent? Yeah, use a refractive index of air, and you'll be able to calculate maybe how much this is going to be bent. Oh, it's going to be bent 2.5 inches. So you reach 2.5 inches to the right outside the water, and guess what? You catch it. Now, I'm not saying that's what the figure is. I'm just giving you a rough example. So the refractive index means nothing for flat Earth. Nothing. Absolutely nothing. We don't take pictures underground, or underwater rather, up into the atmosphere. And the differences in the density are nowhere near what we're going to have in the pool I just showed, where there's no distortion whatsoever. And there's massive difference in the density from the top of that water to the bottom. And yet, did they look curved to you? Did it look like there was distortion? Absolutely not. Because it doesn't matter what the refractive index is as long as you stay within that one medium. Don't go outside the medium. There is no refraction to worry about, period. Those who want to say otherwise are in the cognitive dissonance, or, and I don't mean this in a negative way, they're ignorant of the facts. Guys,
because I want to hear a valid reason why this experiment that we're watching right here, and it's on our channel, anybody can go and look at it and read the comments. It's called the 7.5 mile flat earth laser test on a frozen lake. It was obviously very cold, likely below zero. And like I said, the things you have to consider here is that density altitude was likely identical on each side of the lake. The fact that it was below freezing tells you that the moisture component has been frozen out of the air, crystallized and dropped to the ground point blank. And the fact that he was able to track with that laser beam all the way across the lake, all 8 miles or 7.5 miles across the lake, tells you that, you know, refraction must be absolutely miracle working, you know, for it to be able to do that, except the fact that refraction couldn't be happening because you have identical density altitude on each side of the lake. It's kind of like if you shine a light through a glass of water. If you go on one side and the water is essentially the same temperature, it's going to go straight across. Whereas if you start the light from above it, right, then it's going to hit that denser water and it's going to refract and kick it off to the side. Well, I'm saying that that condition simply would not exist over a lake that's frozen, you know, in the middle of the night. Not going to happen.
Okay, so someone trying to debunk the flat earth will probably try and say that this Toronto skyline is a mirage, but the sun is an exception. Oh no, that's real. There's no mirage there, but we're actually moving away from it, and it's causing it to appear to go down due to the curvature of the Earth. If they are willing to say that this Toronto image is a mirage, refracting light upward, they must be willing to admit that this is also a mirage. But let's say they do, because pictures like this clearly depict that it is a mirage. It's just being refracted the other way, being refracted upward. Then if it is being refracted upward, how can you explain how it appears to set and to sink on the horizon? and then they say, oh, well, that's just the curve. So you can't have it both ways. It's a mirage is causing it to look like that. We know that refraction works in both ways. It can refract up or down. So in this situation, if it appears to dip below the horizon, and you admit that light refraction is at play here, then it must be refracted down. If it were truly the case that it was actually being refracted upward, causing it to look distorted, and then it goes down just due to us rotating away from it, then this should not happen anywhere. Remember, with regards to what you think you learned in school about physics and science, school does not teach you to think critically. It just helps you become better at remembering what other people say about stuff. Now don't misunderstand me though. Light refraction, density, perspective, all very valid. True, real physics. But that doesn't mean all of it is. Truth mixed with lies is a very powerful form of deception. You hear something that really resonates true to you, like density or light refraction, and you believe it. So that when they begin to get deep into the convoluted theory of gravity in the globe, you believe that too, because that professor or teacher said one or two things that you like, and it makes you perceive them and the scientists that they lecture about as being knowledgeable and truthful. For this reason, half-truths are very dangerous. A half-truther can very easily make anyone believe anything that they say just by throwing little bits of truth that really resonate with a person and get them on their side. So take a look at this. This is a prime example of somebody who has really fallen victim to somebody who claims to be speaking the truth, but they're really just half-truths. He thinks that if the earth were flat, then the oceans would spread out, covering all the flat land masses. He can't conceive of the idea that there's different elevations on the plane. He just thinks, oh, flat? Oh, you mean whole thing? Okay. If you say it's flat, then that must mean there cannot be any basins where water can stay. People are programmed.
So all you boys and girls that think that negligible somehow means, well, you only need a couple of degrees to get it round the curve of the Earth, it's bullshit. It's negligible. It isn't worth talking about. In the paper that Mick West cites, refraction is described as not just bending of light down. It's the bending of light in all directions, up, down, left and right. But on Mick West's website, refraction is simply a calculation for down. You can clearly see that the light moves up as well as down. It doesn't just move down. So why is it that ballers use Mick West's bullshit website to tell us to calculate for refraction when they're telling us to calculate for a downward spiral all the time, when you can clearly see that it's an upward thing as well as a downward, and it fundamentally settles back where it started. Calculating for refraction is simply bullshit. It's negligible. It isn't worth talking about. And it certainly isn't going round any curvature of the Earth. Don't listen to any baller, and don't let any baller come back at you with refraction to explain stuff. Because it's simply bullshit. It really is bullshit. It does not bend around the curve of the Earth. Even if there was a curve to the Earth, it wouldn't do it, because it bends up as well as down. This Skunk Bay footage, you can see, it bends up as well as down. Ballers are misrepresenting how little, they're misrepresenting how much light can bend to support their argument. But it doesn't bend. Not the way they say. It bends up as well as down. And calculating for it as a continuous downward streak is simply dishonest.
You're either dead or you're alive. There's no in between.
People are programmed
So people realized that the world is curved.
See if I can find it. Oh, there's the north rack. Look at that. Even got the light flashing on it, on the north rack. And look at the water well behind it. Oh, yeah, baby. Look at the water well behind it. Oh, yeah, baby.